Before the Big Bang, there wasn't darkness, there wasn't emptiness, there wasn't even before. No space to stretch into, no time to tick, no energy to spark, just the total absence of anything that could exist. So if reality began with nothing at all, what lit the first fuse, and what does nothing mean to physics? Picture the universe as a crime scene with the evidence intact, yet the culprit may be the very idea of causation. We can read the afterglow, measure the expansion, and map the debris of creation without knowing what, if anything, struck first. In this documentary, we follow the trail that begins where certainty ends, at the boundary of our best equations. The Big Bang in modern cosmology is not a simple story of an explosion in space. It is a reconstruction from evidence, a careful rewind of cosmic history until the tape grows noisy. Astronomers watch galaxies flee in every direction, their light stretched thin across expanding distance. Satellites listen to the cosmic microwave background, a faint thermal whisper that still carries patterns from infancy. And in the oldest atoms, the universe keeps a chemical ledger: hydrogen, helium, traces of deuterium, signed by a furnace we can no longer visit. Yet when we push these clues back toward the first instance, language itself becomes unstable. Words like cause, trigger, and prior assume a background stage where events line up. If space-time is part of the system being explained, then our usual intuitions may be smuggling in what we're trying to derive. So we will ask a sharper question, not as philosophy, but as physics. What does nothing mean when the vacuum is not empty? In quantum theory, the lowest energy state can still fluctuate, carry structure, and exert measurable pressure on reality. In gravity, even emptiness can bend, expand, and store information in its geometry. Between these frameworks lies a frontier where general relativity and quantum mechanics disagree, and the disagreement is not a footnote. It is the Planck scale, where density and curvature become so extreme that extrapolation turns into guesswork. The infamous singularity is less a destination than a warning sign, an indication that our map ends before the terrain does. From there, one possibility rises like a sudden gust in the early cosmos: inflation, a brief era of accelerated expansion that could smooth the universe and amplify microscopic uncertainty into cosmic structure. But inflation, if it happened, is not a magic origin story. It demands ingredients, fields, and rules already in play. That distinction matters because it separates what our data can test from what our metaphors merely suggest. We will watch the universe cool from an almost featureless blaze into a seething plasma of particles, then into the first stable building blocks. We will follow the handoff from energy to matter during reheating, and confront the puzzle of why anything survived annihilation when matter met antimatter. We will trace how invisible dark matter sculpted the cosmic web, how ordinary atoms fell into those gravitational wells, and how stars forged the elements that later learned to ask questions. All along, we will keep returning to the same disciplined tension: mystery without surrender. Some proposals replace a beginning with a bounce, some replace a boundary with a no boundary, and some suggest that space-time itself may emerge from deeper mathematics. Each idea makes promises, and science demands receipts. That is why this journey is guided by constraints as much as imagination. We will see how tiny temperature ripples in the microwave sky, the phase of primordial sound waves, and the absence, or presence, of certain polarization patterns can rule entire origin stories in or out. We will meet the cracks that remain, like the lithium problem and the Hubble tension, and learn why they are not embarrassments but signposts. By the end, we will not pretend to close the question of the universe from nothing, but we will be able to say exactly where knowledge is solid, where it becomes probabilistic, and where the very meaning of nothing fractures into multiple competing definitions. And in that fracture, a deeper kind of clarity begins to appear, one that does not require final answers to reveal how far evidence can take us. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by defining the paradox, then rebuild the Big Bang from observation, before crossing into the Planck frontier and the inflationary dawn. From there, we follow matter's survival, the rise of galaxies and life, and the hard limits of what physics can claim. Imagine asking what happened before the first moment, then realizing that the word before might not apply at all. The Big Bang is often described as the beginning of space and time, yet our minds keep reaching for a cause that comes earlier, as if time were a stage already built. This tension is the documentary's starting point, and it is more than a philosophical itch. If nothing existed before the Big Bang, how did everything start? And what could start even mean without a clock? If there was no time, what could trigger anything? And what would trigger mean when there is no earlier and later? Cosmology answers with a warning about language, because our words were forged in ordinary experience. Beginning can mean the earliest time our equations describe reliably, where the math still behaves and predictions can be checked. It can also mean the literal start of space-time itself, where the idea of earlier moments breaks down and the question changes shape. In everyday life, causes come before effects, and the ordering feels as solid as the ground. We picture a chain of events stretching backward, link by link into the past, with each link anchored by a prior one. That intuition is powerful, but it is trained inside time, not outside it, and it may mislead us at the edge. Physicists use the word space-time to name what we treat as the arena of events, but it is not merely a backdrop. It is not just space as a container plus time as a clock, because modern physics fuses them into a single geometric structure. In that structure, distances and durations depend on motion and gravity, and even the definition of simultaneous becomes relative. General relativity ties gravity to geometry with a stark elegance that changed science in the early 20th century. Mass and energy curve space-time, and curved space-time guides how mass and energy move, so gravity becomes the shape of the arena itself. When we rewind the cosmic story using these rules, the universe gets hotter and denser, and the familiar cosmos compresses into an earlier, brighter state. That rewind leads to a boundary in our description, and the boundary is not merely a missing page. At extremely early times, densities and curvatures become enormous, and the smooth geometry of relativity is pushed toward extremes. The equations can point toward a singularity, a place where quantities blow up and the model stops making sense, like a map that ends at a cliff. A singularity is not automatically a real thing in nature, even if the mathematics seems to demand it. It is often a signpost that a theory has been pushed beyond its domain, the way classical physics fails inside atoms. It tells us we need a deeper framework, likely one that unites gravity with quantum physics, because the early universe is both intensely gravitational and intensely quantum. So the Big Bang is best introduced carefully, with the discipline that evidence demands. It is the name for an early hot, dense state from which the universe expanded and cooled, leaving measurable traces across the sky. It is not necessarily the claim that the universe began as an infinitely small point, because infinitely small may be a warning label rather than a literal description. This distinction matters because the central question depends on it, and the stakes are conceptual as well as scientific. If the Big Bang is a physical boundary where time begins, before may be undefined in the strictest sense. If it is only the earliest phase we can currently model, there may be earlier physics we have not discovered, waiting behind the boundary like a hidden chapter. Now we confront the hardest word in the title. Nothing is not a single concept in physics, and the difference changes the entire debate in subtle ways. When people say nothing, they often mean empty space, darkness and silence, an unoccupied room of the cosmos with the lights turned off. Empty space is not nothing in modern theory, and that is where intuition first breaks. Even a perfect vacuum is still space-time, with structure, symmetries, and measurable effects that persist even when particles are absent. It can host fields, fluctuations and energy that cannot be removed by simply clearing out matter, because the vacuum is an active state, not a blank one. Quantum field theory treats particles as excitations of underlying fields, like ripples on an ocean that is present even when the surface looks calm. Those fields can exist even when no particles are present, and they fill space as part of the basic description. The lowest energy state of a field is called the vacuum, but it is not featureless, because quantum uncertainty prevents perfect stillness. Vacuum energy is one way to name what remains when everything obvious is removed. In quantum physics, fields fluctuate even in their ground state, because energy and time obey uncertainty relations that forbid complete quiet. Those fluctuations can leave fingerprints, like the Casimir effect, where forces appear between closely spaced plates because the vacuum's allowed modes are constrained by geometry. So we need two definitions on the table, and we need to keep them separate as the story unfolds. Empty space means space-time exists but matter is absent, and fields sit in their vacuum states still governed by laws. Nothing, in the strictest sense, would mean no space-time, no fields, no background, and no laws expressed as dynamics within time, no stage, no actors, and no script. That strict nothing is difficult to even phrase because our grammar smuggles in what it tries to remove. Without space-time, there is no location, no duration, and no background in which events happen, so even the word happen becomes slippery. The usual structure of explanation assumes a timeline, but the timeline is exactly what may be missing, which is why the paradox bites so hard. This is where the paradox sharpens into something almost physical, like pressure building at the edge of thought. We ask for a cause, but causes are relations between events in time, and the relation depends on an ordering. If time begins, there may be no earlier event to serve as a cause in the ordinary sense, and the demand for one may be a category error. Some responses redefine what counts as an explanation, and that move is not a dodge so much as a shift in perspective. Instead of a prior event, the explanation might be a boundary condition, a principle, or a law that selects a history from many possibilities. It might be a quantum description where beginning is not a moment but a condition on a whole space-time, like specifying the shape of an entire path rather than its first step. Other responses argue that nothing is unstable, or that quantum creation is possible, but the details matter. These claims depend on what nothing means in the model, and models often start with a vacuum state, a field, or a quantum wave function. If the model already includes space-time, fields, or a quantum state, it is not the absolute absence people imagine, even if it feels empty by everyday standards. We are not here to settle the debate in one chapter, because the frontier is still open and the evidence is still being interpreted. We are here to make the question precise enough to investigate, which is the first duty of science. Precision is the difference between a mystery we can test and a riddle that only loops, feeding on ambiguity. To do that, we need the evidence that the Big Bang framework is not just a story told to comfort our curiosity. The universe is expanding, and that expansion is measured in the redshift of distant galaxies, a stretching of light as space itself grows. The farther we look, the more the light is shifted toward red, and the more the past looks different, because looking far is also looking back in time. Historically, this was not an obvious conclusion, and it reshaped astronomy in the last century. Observations by Edwin Hubble and others revealed that galaxies are receding on average, and the recession speed increases with distance. In modern terms, the pattern fits a universe whose scale factor changes with time, turning the night sky into a record of cosmic history. Expansion implies a denser, earlier universe when we run the clock backward, and the implication is not merely qualitative. Temperatures rise, particle energies increase, and matter becomes a plasma where electrons and nuclei cannot easily bind. It also predicts a leftover glow from the time the universe cooled enough for light to travel freely, when charged particles stopped scattering photons so efficiently. That glow is the cosmic microwave background, a faint radiation filling the sky, arriving from every direction with remarkable uniformity. In visuals, it is a ghostly afterimage of a younger cosmos, mapped as a sphere around us, like the inside surface of a vast lantern. Discovered in the 1960s and later measured with increasing precision, it turned the Big Bang from a hypothesis into a quantitative science. The microwave background is not just present, it has a precise temperature and pattern that can be measured to many decimal places. It is nearly uniform but not perfectly smooth, and the tiny variations are not noise, they are information. Those slight warm and cool patches map the seeds of later structure, and they match a universe that once behaved like a hot plasma, oscillating under the push of radiation and the pull of gravity. Another clue comes from the simplest elements, and this clue ties cosmology to nuclear physics in a striking way. In the first minutes, the universe was hot enough for nuclear reactions, but it cooled quickly as it expanded. Big Bang nucleosynthesis predicts the abundances of hydrogen and helium, plus traces of deuterium and lithium, because the early universe briefly functioned like a cosmic fusion reactor. Those predictions can be compared with observations in ancient gas clouds and in the oldest stellar populations, where later stellar processing is minimal. The match is not perfect in every detail, and the lithium discrepancy remains a known tension, but the overall agreement is strong. It is strong enough to treat the hot early universe as a tested framework, and it is one of the reasons the Big Bang model became the standard cosmological picture. Structure formation adds a later chapter to the same evidence trail, showing how small beginnings become grand architectures. Galaxies and clusters grew from small early irregularities under gravity, amplified over billions of years as matter flowed into denser regions. Computer simulations and sky surveys reveal a cosmic web of filaments and voids, and the patterns connect the early fluctuations to the large-scale structure we see today. These clues do not directly show a first instant, and they do not photograph the birth of time. They show that the universe was once hotter, denser, and simpler, and that it evolved in a way our physics can track with impressive consistency. They also show where our physics becomes uncertain, and where new ideas must enter, because the trail fades as we approach the earliest fractions of a second. The uncertainty is not a minor technicality, because it sits exactly where our deepest questions live. Near the earliest times, quantum effects of gravity should matter, and our two best theories describe reality in incompatible languages. General relativity treats spacetime as smooth and continuous, while quantum theory treats nature as probabilistic and quantized in key ways, so the early universe forces them into the same room. When we combine them naively, we get infinities and contradictions, and the mathematics starts to signal distress. That is why the singularity appears in simple extrapolations, and why many physicists treat it as a symptom rather than a destination. The real beginning, if there is one, likely requires a quantum theory of spacetime, where geometry itself may fluctuate and classical time may emerge only approximately. This is the narrative stake of the series, and it is also the methodological challenge. To ask whether the universe came from nothing, we must navigate between tested evidence and speculative edges, never confusing one for the other. We must use cosmology to read the sky, particle physics to understand the early plasma, and theoretical physics to ask what spacetime can be when pushed to its limits. We also have to confront what counts as a satisfying answer, because the question is partly about explanation itself. Is an answer a mechanism that occurs in time, like an explosion, a decay, or a tunneling event described step by step? Or can an answer be a principle that makes a universe inevitable, even without a prior moment, an explanation that selects a whole history rather than initiating a first tick? The Big Bang is often misheard as an explosion in pre-existing space, and the misconception is understandable because explosions are how we picture sudden beginnings. In the standard picture, it is the expansion of space itself, with distances growing everywhere as the scale of the universe changes. There is no center in the usual model, and no outside space into which the universe expands, because outside is not part of the description. That idea is already hard on intuition, and the visuals can help if we choose them carefully. Imagine galaxies as dots on a stretching fabric, with every dot seeing others recede, yet with no privileged middle point. Now imagine rewinding that stretching, watching the dots draw closer as the fabric tightens, until the entire visible cosmos becomes a compact, searingly hot state. It gets harder when we ask about the beginning of the expansion, because the question presses on the limits of meaning. If space and time are part of the universe, the question, where did it happen, may be as misplaced as, what is north of the North Pole? Yet the discomfort is productive, because it tells us where everyday categories fail and where new ones are required. But we should not hide behind metaphors, because metaphors can soothe without explaining. The point is not to dismiss the question, but to refine it until it becomes scientifically sharp. We can ask what the earliest describable state was, what laws governed it, and whether the concept of time emerges from something deeper, the way temperature emerges from microscopic motion. We can also ask whether the universe had a prior phase, and here the boundary becomes a research program. Some models propose a bounce where contraction preceded expansion, replacing a singular beginning with a turnaround governed by new physics. Some propose eternal inflation, where our observable region is one bubble in a larger process, and the word beginning applies differently depending on what scale you mean. Even these models do not automatically answer why anything exists, and that is an important restraint. They shift the boundary and they change what beginning means, sometimes replacing a single start with a more complex landscape. They also raise new questions about what is fundamental, what is contingent, and what can be tested, because a model without observational hooks risks becoming a story that cannot be checked. So Chapter 1 ends where the real work begins, with definitions tightened and the evidence placed on the table. The paradox of nothing is not solved by clever wording, but it is clarified by careful distinctions that keep us honest. The Big Bang is a well-supported description of an early hot universe, yet the origin of space-time remains an open frontier, and the frontier is exactly where the word before may dissolve. Next, we follow the evidence backward until the trail fades. We will see exactly what the data demands, where the equations hold, and where the idea of before starts to lose meaning. We start with what can be checked, because origins without evidence become mythology, and mythology is persuasive precisely when it cannot be tested. The Big Bang model is not a single claim about a first spark, or a dramatic moment of creation painted onto a blank canvas. It is a framework describing how the universe was once hotter and denser, and how it expanded and cooled into the cosmos we measure today. In other words, it is an evidence-driven reconstruction, built from light, statistics, and physics, rather than a tale told to satisfy intuition. Chapter 1 warned that before may fail when time itself begins, because before assumes a clock already running somewhere. Chapter 2 narrows the target and asks what the sky already tells us, using observations that can be repeated and improved. If we can map the early universe with data, we can also locate where the map ends, and where inference becomes speculation. That boundary matters, because cosmology is most trustworthy when it admits where it cannot yet speak. The first pillar is cosmic expansion, measured through light that has travelled for billions of years across a changing cosmic distance. In visuals, we begin with a dark sky scattered with galaxies, then we zoom into a single point of light and split it into a rainbow. When astronomers spread that light into spectra, familiar atomic lines appear like barcodes, and those barcodes are shifted toward red. The shift is systematic across the sky and grows with distance, which is exactly what an expanding universe predicts. Even the faintest galaxies carry this signature, as if the universe stamps every photon with its own stretching history. Redshift can mean motion, and in everyday experience it usually does, like the pitch of a siren dropping as it passes. In cosmology, it mainly means stretched wavelengths, because the space the photon travels through is itself expanding. The key idea is expanding space-time, where the distance between galaxies grows even if galaxies sit still locally within their own gravitational neighbourhoods. In that picture, photons lose energy because space expands while they travel, so their wavelength lengthens and their colour slides toward red. The effect is not friction and not fatigue. No medium is draining the light. Rather, the metric that defines distance is changing beneath the photon's path. The details matter, because redshift is not a vague metaphor, and it is not an interpretive flourish. Astronomers identify specific spectral features, such as hydrogen's Balmer lines or calcium's absorption lines, and compare their observed wavelengths to laboratory values. The ratio between the two gives a redshift number, Z, which is a direct measure of how much the universe expanded during the photon's journey. A galaxy at Z^1 is seen when the universe was roughly half its current size, which is a simple statement with deep consequences. At higher redshifts, the interpretation becomes even more dramatic, because we are not merely looking far away. We are looking into a smaller, younger universe. The Hubble, Lemaitre law captures the pattern in one relation, and it emerged from a historical convergence of theory and observation. In the 1920s, Edwin Hubble used Cepheid variable stars to estimate distances to nearby galaxies, while Georges Lemaitre connected redshift to an expanding solution of Einstein's equations. Recession speed increases roughly in proportion to distance, so farther galaxies show larger redshifts, and the slope of that line is the expansion rate today. The law is not a mere historical curiosity, because it anchors the entire cosmic timeline and calibrates how quickly space is stretching now. It also quietly reshaped humanity's self-image, because it replaced a static cosmos with one that has a measurable history. That expansion rate is encoded in the Hubble constant, and it sets the universe's timescale in the same way as speed sets a travel time. If the expansion had always been the same, its inverse would approximate the cosmic age, like estimating how long a road trip took from distance and speed. In reality, the rate changes, because gravity slows expansion when matter dominates, and dark energy speeds it up later. The age must therefore be inferred with a full model that tracks how the expansion rate evolved across cosmic history. This is why cosmology is not just measuring one number, it is reconstructing a curve, and the curve carries the story. The expansion is not galaxies flying through pre-existing emptiness like shrapnel, and the difference is more than philosophical. It is the metric itself evolving, changing what we mean by distance over time, which is why the same equations describe every direction with no preferred center. This is why every observer can see others receding without any central point, because the expansion is not something happening from a place. In visuals, we can show a grid drawn on space itself, stretching smoothly as galaxies remain fixed on the grid, like dots on an inflating sheet. Then we can cut to a close-up where galaxy groups stay bound, because gravity locally resists the global stretching. A useful check is consistency across methods, because one dataset can mislead and one instrument can drift. Distances can be estimated with supernovae, galaxy surveys, and standard rulers in the early universe, each with different systematics and different assumptions. Type Ia supernovae act as standardizable candles, because their peak brightness correlates with how quickly they fade, letting astronomers infer distance from observed flux. Galaxy surveys provide statistical patterns, and the early universe provides standard rulers through sound waves frozen into matter. When these methods converge, expansion becomes a measured property, not an assumption we smuggle into the story. When they disagree, the tension is informative, like a compass needle that twitches near hidden iron. Expansion also implies a past that was denser and hotter, because the same matter and radiation occupied less volume and had less room to dilute. Run the equations backward and temperatures rise, particle energies increase, and matter becomes ionized plasma, meaning electrons are not bound to nuclei. The universe becomes opaque, because photons scatter off free electrons in a process called Thomson's scattering, bouncing like pinballs through a fog. In visuals, the cosmos shifts from transparent darkness to a bright milky haze where no line of sight can travel far. It is a universe with light everywhere, yet no clear view, radiance without visibility. That opacity matters because it predicts a specific relic, and relics are where cosmology becomes almost forensic. When the universe cooled enough for electrons and nuclei to form neutral atoms, light decoupled from matter and began travelling freely across expanding space. That transition is called recombination, though it is really the first time stable atoms formed in large numbers. Those photons should still exist, stretched by expansion into microwaves, arriving today as a faint, cold afterglow from all directions. The prediction is strikingly concrete. If the hot early phase is real, then the sky must still carry its cooled thermal echo. The second pillar is the cosmic microwave background, the CMB, and it is one of the most striking successes of prediction meeting observation. It is a nearly uniform bath of radiation arriving from every direction, not from stars, not from galaxies, but from the sky itself. Its spectrum is an almost perfect blackbody, with a temperature near 2.7 Kelvin, meaning it matches the curve expected from thermal radiation in equilibrium. In visuals, we move from a night sky to a false-coloured dome of radiation, as if the universe has a hidden thermal skin. Even the emptiest patch of sky glows in microwaves, and that glow is older than any star. A blackbody spectrum is a strong clue because it signals thermal equilibrium in the past. An equilibrium is hard to fake across the entire sky. It means the early universe behaved like a hot, dense fluid of matter and radiation, where photons, electrons, and baryons exchanged energy rapidly. It also means the CMB is not starlight scattered by dust, because dust and stars cannot produce a spectrum this smooth and precise. The blackbody curve is a fingerprint, and it points to a specific era when the universe was hot enough to thermalize radiation efficiently. The spectrum is so precise that it behaves like a laboratory result, except the laboratory is the entire cosmos. The CMB was predicted before it was found, which is rare in cosmology where many ideas are post hoc explanations. In the 1940s, George Gamow and collaborators argued that a hot early universe should leave behind a cooled radiation background. It was detected accidentally in 1965 by Arno Penzias and Robert Wilson, who were trying to eliminate a persistent microwave hiss in their antenna. The story is often told with humour, including the famous cleaning of pigeon droppings from the equipment. But the scientific point is serious. The sky itself was glowing. In that moment, the universe stopped being merely ancient. It became observable in its infancy. Then the measurements became precise, and precision is where the model becomes constrained rather than merely plausible. Satellites like COBE confirmed the blackbody spectrum with extraordinary accuracy, showing deviations smaller than parts in 10,000. Later missions like WMAP and Planck mapped the tiny temperature variations across the full sky, turning a uniform glow into a structured pattern. Each generation of data tightened the model and reduced the room for alternatives, because the CMB is not one number, but a field of information. The map is also a time capsule, because every pixel is a line of sight to the same early epoch. Uniform does not mean featureless, and the deviations are the real treasure because they encode the early universe's initial conditions. The CMB has tiny anisotropies at the level of tens of microkelvin, which is a whisper compared to its 2.7 Kelvin mean. Those temperature differences trace density variations in the early plasma, along with subtle velocity flows and gravitational redshifts. In visuals, the smooth sphere resolves into mottled patches, like a faint cosmic weather map with hot and cold spots. The pattern looks almost casual, yet it is the earliest detailed portrait of our universe that physics allows. Those variations are small, but gravity amplifies small differences over time, and that amplification is the engine of cosmic structure. Denser regions attract more matter, becoming the seeds of galaxies and clusters, while underdense regions become cosmic voids. The CMB is therefore not only a relic of heat, but a blueprint for structure, showing the universe's initial texture. It is a snapshot of the universe when it was about 380,000 years old, long before the first stars ignited. It also tells us something unsettling. The universe began remarkably smooth, but not perfectly smooth, just uneven enough for everything we see to grow. The anisotropy pattern is not random, because physics imprinted a characteristic scale that can be calculated and then checked against data. Before decoupling, gravity tried to compress matter while radiation pressure pushed back, and that tug of war created sound waves in the plasma. These are acoustic oscillations, actual pressure waves propagating through the early universe's ionized fluid. When atoms formed and photons decoupled, the oscillations froze in place, leaving rings and peaks in the statistical pattern we observe today. In visuals, we can show ripples expanding in a glowing plasma, then abruptly locking into a fossil pattern as the universe turns transparent. The peaks in the CMB power spectrum encode geometry and composition, and the translation from map to spectrum is a triumph of mathematical modelling. Their positions test whether space is flat, open, or closed on large scales, because geometry changes how a fixed physical scale appears on the sky. Their heights reveal how much matter is normal, how much is dark, and how much is in radiation, because different components respond differently to compression and pressure. Even the relative odd and even peaks carry information, reflecting how baryons load the oscillations and change the balance between compression and rarefaction. What looks like a jagged graph is, in practice, a census of the cosmos. The CMB also carries polarization, which adds another layer of constraints and turns intensity maps into a richer dataset. Polarization arises because photons scatter off electrons in a way that depends on direction, and a quadrupole pattern in the radiation field imprints a preferred orientation. Polarization patterns track the motion of the plasma, and later scattering by rionized gas, when early stars rionized hydrogen and reintroduced free electrons. They also offer a possible window into primordial gravitational waves through so-called B modes, though that signal remains contested and difficult to separate from foreground dust. In visuals, the temperature map gains faint vector-like strokes, revealing hidden structure in the same ancient light. At this point, the evidence is already heavy, but the story gains depth when we add a third pillar that comes from nuclear physics, not telescopes alone. In the first minutes, the universe was hot enough for fusion, but it cooled fast as expansion diluted the energy density. That brief window produced light nuclei in predictable ratios, and those ratios are sensitive to conditions we can model with known physics. In visuals, we shift from galaxies and maps to a stylized early universe, glowing white-hot, where protons and neutrons collide in a dense, rapidly cooling bath. The scene should feel urgent, because the universe is racing against its own expansion. Big Bang nucleosynthesis explains why the universe is mostly hydrogen and helium, and it does so with a timeline that is surprisingly specific. It predicts a helium mass fraction near 1/4, with most of the rest as hydrogen, because neutrons get locked into helium efficiently once deuterium can survive. It also predicts deuterium and helium-3 in trace amounts, plus a small amount of lithium-7, produced through a network of reactions involving beryllium. The key is that the universe expanded quickly, so nuclear reactions froze out before heavier elements could form in bulk. In plain terms, the cosmos had the heat for fusion, but not the time. These are not adjustable storytelling details, because the reactions depend on measured cross-sections and on well-tested nuclear physics. The outcome depends mainly on the baryon density, the amount of ordinary matter, because density controls how often nuclei collide before the universe cools too much. Change that density and deuterium and helium shift in ways observations can test, which makes nucleosynthesis a quantitative probe rather than a qualitative narrative. Even the neutron lifetime matters, because it sets how many neutrons survive long enough to be captured into helium. The early universe becomes a kind of natural reactor experiment, and the abundances are its readout. Deuterium is especially sensitive, so it acts like a cosmic baryometer, a gauge of how many baryons existed per photon in the early universe. If baryon density is higher, deuterium gets burned more efficiently into helium, so the leftover deuterium abundance drops. Measurements in pristine gas clouds at high redshift can approximate the primordial value, because such clouds have undergone minimal stellar processing. Astronomers look for deuterium absorption lines in quasar spectra, where distant quasars backlight intervening gas like a flashlight through mist. In visuals, thin dark notches appear in a bright quasar spectrum, and each notch becomes a number that weighs the early universe. When matched to nucleosynthesis calculations, those deuterium measurements pin down the baryon fraction with surprising precision, and the precision is part of the drama. It means we can estimate how much ordinary matter exists in the entire observable universe from a few spectral lines and a nuclear reaction network. That baryon fraction can then be compared with the CMB's independent estimate, which comes from how baryons affect acoustic peaks. The agreement is one of the strongest internal consistency checks in cosmology, linking the first minutes to the first 380,000 years with the same underlying parameters. It is hard to overstate the implication. Two radically different kinds of evidence converge on the same cosmic inventory. Lithium is the famous complication, and it matters because it shows the model is not perfect and because imperfections can be clues. Observed lithium in old, metal-poor stars is lower than the simplest predictions, a mismatch sometimes called the lithium problem. The tension could reflect stellar physics, such as lithium being destroyed or diluted in stellar atmospheres, or uncertainties in nuclear rates. It could also hint at new early universe effects, and it remains a live problem precisely because the rest of the framework fits so well. In a strange way, lithium plays the role of an honest crack, small enough to study but persistent enough to demand attention. Together, expansion, the CMB, and nucleosynthesis form a triangulation, and triangulation is how uncertain landscapes become navigable. They point to a universe that began in a hot, dense state, and then cooled as it expanded, and they do so from 3 different eras and 3 different kinds of evidence. They also constrain the contents of the universe, because the same parameters must satisfy all 3 pillars at once. When you force that consistency, the constraints lead to a surprise that is now central to modern cosmology. The universe, it turns out, is not only bigger than we imagined, it is also stranger in what it is made of. The surprise is that ordinary matter is not most of what gravitates, and the evidence appears first in places where gravity reveals itself more honestly than light. Galaxies rotate too fast for their visible mass, meaning stars far from the centre orbit at speeds that should fling them outward if only luminous matter were present. Clusters of galaxies bend light more than their stars allow, producing gravitational lensing arcs and distorted background galaxies. The simplest reading is additional matter that does not emit or absorb light, matter that is present because gravity insists it must be. In visuals, we can overlay a luminous galaxy image with a larger ghostly halo, showing mass extending far beyond the stars. Dark matter is a name for that missing gravitational mass, not a single confirmed particle, and the name is deliberately modest. It behaves as cold and collisionless in the simplest models, meaning it moves slowly compared to light, and rarely interacts except through gravity. That behavior helps explain how structure formed early without being erased by radiation pressure, because baryons were tied to photons before recombination. In simulations, cold, dark matter forms filaments and halos, and the visible galaxies appear later as bright knots within that invisible scaffolding. The phrase dark can mislead. because it is not darkness like a shadow. Rather, it is matter that refuses to announce itself except through its pull. In the early universe, baryons were coupled to photons and could not clump efficiently, because radiation pressure resisted gravitational collapse. Dark matter could start collapsing earlier, forming potential wells that deepened over time as matter streamed inward. After decoupling, ordinary matter fell into those wells, accelerating galaxy formation and allowing stars to ignite relatively early. This sequence is not just a story, because it leaves signatures in the CMB, in galaxy clustering, and in the distribution of matter inferred from lensing. The universe's large-scale architecture, the cosmic web, looks like a gravitational memory of those early invisible wells. The evidence for dark matter is not one measurement, but a converging set that points in the same direction from different angles. Rotation curves show extra mass in galaxies, gravitational lensing maps mass where little light exists, and cluster dynamics reveal missing gravity through the motions of galaxies and hot gas. The CMB also points the same way, because the acoustic peak pattern requires more gravitating matter than baryons provide. Simulations of the cosmic web fit better when dark matter dominates the mass budget, producing large-scale structure that resembles what surveys actually see. Each line of evidence has its own weaknesses, yet together they behave like witnesses who never met and still tell the same story. Yet dark matter is not the only invisible component, because expansion itself carries another shock that arrived late in the 20th century. Distant supernovae appeared dimmer than expected in a decelerating universe, implying they are farther away than a matter-only cosmos would predict. The best fit is that cosmic expansion has been accelerating for the last several billion years, meaning the expansion rate is not merely coasting but speeding up. In visuals, the cosmic scale factor curve bends upward, and the universe's recent history takes on an unexpected twist. The surprise is psychological as much as scientific, because gravity was expected to slow the expansion down. Acceleration implies a form of energy with negative pressure in general relativity, because pressure contributes to gravity in Einstein's equations. Dark energy is the label for whatever drives that effect in the equations, and the label is honest about our ignorance. The simplest version is a cosmological constant, a uniform energy density of empty space, the same term Einstein once introduced and later regretted. If it is truly constant, it does not dilute as the universe expands, so it eventually dominates over matter and changes the long-term behavior of the cosmos. In plain language, the emptiness itself behaves as if it has weight, yet it pushes rather than pulls. Dark energy changes the universe's fate because it competes with gravity on the larger scales, and because it sets the ultimate horizon of what can be seen. If it stays constant, expansion continues accelerating and distant galaxies slip beyond our horizon, leaving future observers with a darker, emptier sky. If it evolves, the future could differ, and measurements aim to detect that evolution through subtle changes in the expansion history. The mystery is sharpened by the fact that the observed value is extremely small in particle physics terms, yet not zero, which makes it feel both delicate and profound. Why should the vacuum be so quiet, and yet not silent? Dark energy also changes how we infer the past, because the expansion rate is not fixed, and because different components dominate at different times. To reconstruct cosmic history, cosmologists fit a model to multiple datasets, and they test whether one set predicts the others. The CMB, baryon acoustic oscillations, and supernovae together constrain the expansion curve, each covering different redshift ranges and different physical processes. When the model works, it feels like a single narrative stitched across billions of years, with the same parameters echoing through every epoch. The elegance is real, but it is also conditional, dependent on the assumption that the same physics applies across the whole span. Here the story gains tension because the model becomes both powerful and fragile, and that duality is part of its character. Powerful because it predicts many observables with a small set of parameters, turning the universe into something like a solvable system. Fragile because the parameters imply that most of the universe is made of unknown components, and unknown components always invite doubt. The triumph is not that everything is understood, but that the unknowns are constrained tightly enough to be named and measured. It is a strange victory. We have numbers for things we cannot yet touch. Even the Hubble constant itself has become a pressure point, and this pressure is felt in the way different methods disagree by more than their stated uncertainties. Local distance ladders, built from parallax to Cepheids to supernovae, yield one value, while early universe inferences from the CMB yield another. The mismatch could be systematic error, a subtle bias in calibration, dust, or selection effects that masquerade as new physics. Or it could hint at new physics beyond the standard model, altering the early expansion rate or the behavior of dark energy. In visuals, two error bars hover close but not overlapping, like a small gap that refuses to close. Still, the core claim of a hot early phase is not hanging on one disputed number, and this is crucial for keeping the narrative grounded. Expansion. The CMB's blackbody spectrum and primordial element abundances are hard to erase, because they are independent and mutually reinforcing. Alternatives must reproduce all three at once, and few do without reintroducing similar ingredients under different names. The Big Bang model survives not because it is fashionable, but because it keeps passing tests that were designed to break it. A robust theory is not one that avoids danger, it is one that survives contact with measurement. Now we clarify what the Big Bang is, because the words still mislead, and language can smuggle in the wrong picture. It is not an explosion at a location in space, with debris flying outward into a pre-existing void. It is a change in the scale of space everywhere, described by a time-dependent metric, where distances between unbound objects grow as the universe evolves. The bang is not a sound or a blast, but a shorthand for a hot, dense state followed by expansion. If we must keep the metaphor, then the universe is not a bomb. It is a stretching fabric whose history can be read in light. It also is not automatically a claim about an absolute beginning from literal nothing, even if popular imagery often suggests that. The evidence points to a hot, dense past, but it does not by itself describe the first instant or what, if anything, preceded it. The model is strongest where it can be tested, and weakest where tests are impossible, which is why careful cosmology separates measurement from extrapolation. The boundary between them is not a failure, but a sign of intellectual honesty. It is also an invitation, because boundaries are where new theories must earn their place. When we extrapolate backward, densities rise and timescales shrink, and familiar matter changes phase as conditions intensify. At about 1 second, the universe is a nuclear reactor for light elements, with neutrinos streaming freely and setting part of the energy budget. A few minutes later, nucleosynthesis winds down as the temperature drops and reactions freeze out. At 380,000 years, it becomes transparent and releases the CMB, and the universe shifts from an opaque plasma to a cosmos where light can travel long distances. In visuals, we can compress this history into a timeline that accelerates, as if the early universe is a fast-forwarded storm. Go earlier than that and we enter particle physics at energies beyond laboratories, where the known forces behave differently, and the particle soup becomes more exotic. Quarks and gluons roam in a plasma, then later confine into protons and neutrons as the universe cools through the quantum chromodynamics transition. Symmetries may break, generating masses and shaping the particle zoo, including the balance between matter and antimatter that must have tilted early. Even if the broad outline is understood, the details are constrained indirectly, which is why this region feels both scientific and mysterious. We are reading traces, not watching footage, yet the traces are consistent enough to be taken seriously. Go earlier still, and the extrapolation approaches a boundary called the Planck Epoch, where our familiar equations begin to lose their authority. At around 10⁻43 seconds, quantum fluctuations of spacetime should be unavoidable, and the very notion of a smooth geometry may fail. Our equations do not reliably describe what happens when gravity is both strong and quantum, because we lack a complete theory that unifies general relativity with quantum mechanics. In visuals, the smooth grid of spacetime becomes grainy and turbulent, as if the fabric itself is boiling. The closer we push, the more the mathematics sounds like a warning rather than a description. General relativity treats spacetime as smooth geometry, and it predicts singularities in simple backward evolution, where density and curvature diverge. Quantum theory treats fields as uncertain and quantized, and it resists infinite densities by making exact values physically suspect. Put them together naively and the mathematics signals break down, not because nature must contain infinities, but because the tools are being used beyond their range. This is where a confident curve on a graph becomes a question mark, and the question mark is earned. It is also where humility becomes part of the method, because overconfidence would be unscientific. A singularity in the equations is not a filmed event, and it is not automatically a real object sitting at the beginning like a cosmic dot. It can be a warning that the model has been pushed past its domain, the same way fluid equations fail inside an atom-scale shock. It tells us the evidence backstory ends before the deepest origin question begins, which is both frustrating and clarifying. The universe gives us a trail of clues, but it does not promise a final scene we can watch. The most honest narration, then, is one that lets the unknown remain visible. This is where the central question returns with sharper edges, because the words we use, before, nothing, beginning, are built for everyday time. If nothing existed before the Big Bang, what does before even mean near the Planck boundary, where time may not behave like a simple line? If space-time is emerging, then nothing might be a boundary condition, not an empty room waiting to be filled. The question becomes less like asking what happened yesterday, and more like asking what it means for a story to have a first page. And if our language breaks here, is that a limitation of the universe, or of the minds trying to describe it? We can now state the chapter's conclusion without solving the mystery, and without pretending the evidence answers more than it does. The Big Bang is evidence for an evolving universe that was once hot and dense, and the evidence is diverse enough to be cross-examined. That evidence points back toward a regime where our physics breaks, and where new principles must take over, whether they modify space-time, matter, or the meaning of time itself. The unknown is not an embarrassment here, because it is precisely where the next testable ideas must aim. What matters is that the edge is real, and we can approach it with disciplined curiosity. Next, we follow the evidence right up to that breaking point, and we ask what theories dare to cross it. We keep the line clear between what is measured, what is inferred, and what is still only a disciplined guess, because the difference is the heart of scientific narration. The map is real, the edge is real, and beyond that edge, the universe becomes a question we have not yet learned to phrase correctly. We have followed evidence backward until the trail thins into theory, and the theory itself begins to fray under scrutiny. The central question returns under pressure, because it refuses to stay philosophical when the equations start to fail. If nothing existed before the Big Bang, what could physics even mean in that absence? If time begins, what could count as a cause when before is no longer defined? Chapter 2 ended at a boundary where our tested equations lose authority, even though their predictions elsewhere are astonishingly precise. Chapter 3 steps into that boundary carefully, because this is where language and math can both mislead. We're not describing a filmed first instant, with a camera hovering outside the universe, watching a clock that has not started. We are marking the earliest regime where our best frameworks collide, and where their collision becomes the story. The name for that regime is the Planck Epoch, a label for the first fractions of a second after extrapolation reaches its limit. It is not a confirmed era with direct observations, like the cosmic microwave background or primordial nucleosynthesis. It is a boundary inferred from dimensional analysis, from the structure of physical constants, and from the known limits of our theories. In practice, it is the point where the mathematics stops being a reliable map, even if it still looks like a map. Planck time is about 10 euros to 43 seconds, the scale where quantum gravity should matter in a decisive way. Planck length is about 10 euro to 35 meters, a scale where the notion of distance may stop behaving classically. Planck energy is about 10 neuron, 19 GeV, far beyond any particle accelerator, and it signals when gravity becomes as strong as other forces. At those energies, even a tiny region would curve spacetime intensely, because energy itself becomes a gravitational source. These numbers come from combining the speed of light, Planck's constant, and Newton's gravitational constant into natural units. That construction is not arbitrary, because it forces quantum effects and gravitational effects into the same expression. When those constants meet, they define a threshold where neither quantum theory nor general relativity can safely ignore the other. It is a kind of dimensional crossroads, where familiar approximations stop being mutually consistent. These numbers are not magic constants that nature must respect like a cosmic speed limit painted on reality. They are warning markers that tell us when our current descriptions become unreliable. They say that space-time itself may need a quantum description, not just the matter and radiation inside it. They also hint that the very idea of scale may change, because scale is normally defined using the geometry we are questioning. In general relativity, space-time is smooth geometry, and gravity is curvature described by Einstein's field equations. In quantum theory, fields fluctuate, and outcomes are probabilistic, even when the underlying equations are exact. push both into the same corner of parameter space, and the assumptions behind each theory begin to contradict the other. The conflict is not a minor technicality. It is a disagreement about what counts as a measurable, well-defined quantity. General relativity assumes a differentiable manifold, meaning you can zoom in and still define smooth distances and smooth curvature. Quantum theory, by contrast, insists that at small scales the very quantities you want to measure cannot be pinned down simultaneously. If energy and time, or position and momentum, cannot both be sharp, then the geometry sourced by energy may also refuse to stay perfectly smooth. The measurement you would need to define curvature precisely would inject enough energy to distort the region being measured. This is why the word singularity appears when we rewind the classical equations toward earlier and earlier times. Density and curvature can diverge, and time can seem to run into a mathematical wall. But a singularity is best treated as a warning label, not as a literal point of infinite density sitting inside nature. It is the model's way of confessing that it has been pushed beyond its jurisdiction. A singularity in relativity is not merely something very dense, but a signal that geodesics cannot be extended in the classical spacetime description. In plain terms, the model stops giving you a complete story for what world lines do. The equations are still written on the page, yet the objects they describe are no longer well defined. The geometry becomes so extreme that the notion of a path through spacetime loses its usual meaning. Infinities in physics usually mean a model is being used outside its domain, even if the model is otherwise brilliant. Classical electromagnetism once predicted infinite self-energy for point charges, and quantum theory changed the rules. Fluid equations can predict infinite gradients at shocks, and microscopic physics resolves the structure. A cosmological singularity may be the same kind of signal, pointing at missing microphysics. The embarrassment is often a clue, because nature tends to stay finite while our approximations do not. Historically, this is how progress often looks at first, an embarrassment in the mathematics that later becomes a doorway. When Planck introduced his constant in 1900, he was patching a problem in blackbody radiation, not reinventing reality on purpose. When Einstein wrote general relativity in 1915, he did not set out to predict a beginning of time, yet the equations implied it under broad conditions. Even the early reception of the Big Bang was cautious, because a beginning sounded uncomfortably like philosophy disguised as physics. So the first task is restraint, because the temptation is to turn a boundary into a narrative. The Big Bang model is evidence for an early hot, dense state supported by expansion element abundances and the microwave background. It is not evidence that the universe began as an actual mathematical infinity. The singularity is where the map ends, not where nature must become absurd. The honest move is to treat the singularity as a sign that a deeper description should take over. The Planck boundary also forces a sharper definition of nothing, because nothing is a word that changes meaning as you zoom in. In everyday speech, nothing means empty space, a dark room with the lights off. In physics, empty space is still space-time, still governed by laws and still filled with fields in their lowest energy states. Even a perfect vacuum, if it is a vacuum in the technical sense, is already a structured physical object. Quantum field theory replaces the idea of particles as tiny objects, with fields that exist everywhere, even where no particles are detected. An electron is an excitation of the electron field, not a bead that always has a definite position. A photon is an excitation of the electromagnetic field, a ripple in something that permeates the universe. Even when there are no particles, the fields remain, and their ground state is called the vacuum. This is why empty space is not a blank stage, but a special configuration of the stage itself. A quantum vacuum is not a container with all the contents removed, like a jar pumped down to emptiness. It is a specific physical state of fields, defined by symmetries and by minimum energy conditions. It can have measurable effects, because quantum uncertainty prevents fields from being perfectly still. In relativistic field theory, the vacuum is also the reference state from which particles, forces, and interactions are defined. To visualize this, imagine a perfectly calm ocean that still carries microscopic ripples because the water molecules never stop moving. The vacuum is calm in the sense that it contains no real particles, yet it is restless in the sense that the field amplitudes cannot be pinned to exact zero everywhere. That restlessness is not a metaphor because it appears in calculations and in experiments. If the camera could zoom into empty space, it would find a statistical texture rather than a featureless black. Zero-point energy is the irreducible jitter of a quantum system in its ground state, even at absolute zero temperature. For a field, that jitter appears as fluctuations in the field amplitude at every point, across a spectrum of wavelengths. In many calculations, the absolute value of vacuum energy can be shifted without changing local physics, which is why the concept is subtle. But differences in vacuum energy can gravitate, and in cosmology that subtlety becomes unavoidable. The universe, unlike a laboratory, cannot always ignore the bookkeeping choice of what counts as zero. Vacuum energy is sometimes described as energy of empty space, and that phrase is both useful and dangerous. It is useful because it captures that emptiness can have physical properties, including pressure and gravitational influence. It is dangerous because it suggests a simple reservoir that can be tapped freely, as if the vacuum were a battery waiting to be drained. In reality, vacuum energy is tied to the state of fields, and changing that state is constrained by dynamics and conservation laws. The vacuum is also not the same as absolute nothing, and that distinction is more than wordplay. A vacuum assumes space-time exists, providing the stage on which fields are defined. It assumes fields exist with equations that tell you what ground state means. It assumes a framework of laws that defines what energy is in the first place. If we remove the stage, the actors, and the script, what remains is no longer a vacuum in any standard sense. This distinction matters because many popular claims about a universe from nothing begin with a quantum vacuum. They begin with a state that is already something in the strict sense, even if it is the emptiest something we know how to describe. The central question asks about no space-time, no fields, no time parameter, and no background in which fluctuations occur. When those ingredients are missing, even the grammar of physics starts to strain. Still, the quantum vacuum is the closest thing physics has to an operational version of emptiness, the kind you can calculate with. It is what remains after we remove particles and radiation as completely as possible. It is the baseline state that experiments and calculations reference, and it is not inert. In the laboratory, we learn about the vacuum indirectly, through shifts, forces, and correlations that would not exist in a truly classical void. Quantum fluctuations are the next key idea, and they are often oversold in the retelling. The uncertainty principle limits how sharply certain quantities can be defined at once, and it does so with mathematical precision. In field theory, that means the vacuum has fluctuations, and those fluctuations can be described as temporary excitations. More precisely, the vacuum has non-trivial correlations, and those correlations show up in how fields respond to disturbances. A common shorthand says energy can appear from nothing for a short time, and it is easy to see why that story sticks. The more careful statement is that energy is not sharply defined over short times in certain quantum contexts, and that vacuum correlation functions are non-zero. Virtual particles are bookkeeping devices in perturbation theory, not literal particles popping in and out like sparks in a void. The diagrams are powerful, but they are not photographs of microscopic events. If you could see the vacuum the way a simulation might render it, it would not look like empty blackness. It would look like a seething texture of correlations, with fluctuations at many scales layered on top of one another. Yet those fluctuations do not hand you free energy on demand, because they are constrained by conservation laws and by the structure of the quantum state. The vacuum is active, but it is not a loophole that lets physics cheat. The vacuum can produce observable effects when boundary conditions change what fluctuations are allowed, which is where the abstract becomes physical. The Casimir effect is one example, where two close plates experience an attractive force due to altered vacuum modes. This demonstrates that vacuum fluctuations are not merely philosophical. They can push on matter. The force is small, but it is stubbornly real, and it reminds us that empty depends on context. The effect is tiny, but it is measurable, and its existence is a reminder that nothing has a spectrum. Change the geometry, change the allowed wavelengths, and you change the vacuum energy difference between configurations. In a universe where gravity responds to energy, even small differences can matter when magnified across cosmic scales. When the entire cosmos is the system, there is no external environment to dismiss as irrelevant. But none of this automatically implies that a universe can be created from a vacuum fluctuation, and the gap between those ideas is crucial. A fluctuation in a pre-existing spacetime is not the creation of spacetime itself. A fluctuation described with time evolution already assumes time exists, because temporary is a time-based word. The seductive phrase "from nothing" often hides a quiet assumption that there is already a stage on which from can occur. So we have to separate three claims that are often blended into one dramatic sentence. Claim 1 is that empty space is physically active, with measurable quantum properties. Claim 2 is that quantum processes can produce particles from fields under the right conditions, including in strong fields or curved spacetime. Claim 3 is that the entire universe can originate as a quantum event from absolute nothing. Only the first two are directly grounded in established frameworks. The third is a frontier question, and frontiers demand careful language. When cosmologists talk about the earliest times, they often use effective field theory, because it is the tool that has earned our trust. They assume spacetime is approximately classical, then add quantum fields on top, and then compute how those fields behave. This works remarkably well for much of early universe physics, including the plasma era and the formation of primordial perturbations. It likely fails at the Planck epoch, where spacetime itself should fluctuate. The failure is expected, not embarrassing, because effective theories are designed to break when the underlying degrees of freedom change. At that boundary, candidate ideas appear, and each tries to replace the singularity with a quantum description that stays finite. Quantum cosmology treats the universe as a quantum system, described by a wave function rather than a classical trajectory. The goal is not to add quantum corrections to a classical beginning, as if the beginning were otherwise intact. The goal is to make the beginning itself a quantum boundary condition. Instead of asking for a single history, it asks for a rule that assigns probabilities to possible histories. The historical background here matters, because these ideas did not appear in a vacuum of speculation. As quantum mechanics matured through the 1920s and 1930s, and as relativity reshaped gravity, physicists began to ask whether the universe as a whole could be quantized. By the late 20th century, the question became unavoidable, because the classical singularity sat like a thorn inside the most successful gravitational theory we have. The rise of particle cosmology and precision measurements made the early universe feel less like myth, and more like a laboratory, at least in principle. One proposal is the Hartle, Hawking no-boundary idea, where the universe has no initial edge in the usual time direction. In that picture, time behaves like a spatial dimension near the origin, and the geometry is smooth rather than singular. Another is the Vilenkin tunneling proposal, where the universe can tunnel into existence from a state with no classical space-time. Both ideas try to keep the mathematics finite, while still recovering the expanding universe we observe. These proposals are not settled facts, and they are not simple slogans once you look closely. They are attempts to write a consistent quantum description when classical time cannot be assumed. They also raise a hard interpretive question. If time is part of what emerges, what does tunneling even mean without an external time parameter? The word tunnel evokes motion, yet the formalism may be closer to a relationship between boundary conditions than a sequence of events. In ordinary quantum mechanics, tunneling is a process in time, with a system evolving from one configuration to another. In quantum cosmology, the language shifts, because there may be no external clock to watch. The wave function assigns amplitudes to entire geometries and field configurations, and the transition can be a relation between boundary conditions, not a movie of events. The mathematics can still be rigorous, but the mental picture becomes slippery. This is where the documentary's hook becomes literal again, because our intuitions are built for stories with sequences. Imagine a time when there wasn't even time, then ask how quantum theory operates without a clock. Some approaches treat time as emergent from correlations between degrees of freedom, where one part of the system plays the role of a clock for another. Others treat the wave function as describing a timeless ensemble, where classical time appears only in semi-classical limits. In either case, before becomes a derived concept, not a primitive one. Even the word beginning starts to wobble here, because it smuggles in an arrow of time. If the fundamental description is timeless, then earlier may be an emergent ordering, not a primitive fact. Yet the universe we observe does have a strong arrow, from hot and smooth toward cooler and structured, so any deep theory must explain how that arrow appears. The question is not only why there is something, but why that something unfolds in a particular direction. Another family of ideas suggests that space-time itself is not fundamental, and that is a radical shift in what we mean by geometry. In these approaches, geometry emerges from more basic degrees of freedom, like entanglement patterns, networks, or discrete building blocks. The Planck length then becomes a scale where the smooth approximation breaks, not necessarily a smallest possible length in a naive sense. It is the scale where the pixels of geometry, whatever they are, can no longer be ignored. Loop quantum gravity, for example, proposes quantized geometry, with areas and volumes taking discrete spectra rather than continuous values. In some loop-inspired cosmological models, the Big Bang singularity is replaced by a bounce, where contraction reaches a maximum density then reverses. String theory offers other possibilities, including extended objects that soften short-distance behavior and dualities that relate seemingly different descriptions. Each approach is an attempt to keep the physics finite, while still matching the universe we can test. In these pictures, the singularity is not treated as an object you could point to on a timeline. It is treated as a symptom of missing microphysics of space-time, like a pixelated image that looks smooth only from far away. When you zoom in past the resolution limit, the smooth curve breaks into something else, and the old description stops applying. The visual metaphor is useful, but the real demand is mathematical, a theory that tells us what replaces the continuum. These frameworks differ in details, and none is yet confirmed by direct evidence, which is why the tone must stay exploratory. But they share a theme that keeps resurfacing. The singularity is not treated as a destination. It is treated as a signpost that says, in effect, new rules required here. The rules may be discrete, probabilistic, or emergent, but they must reproduce the familiar world when the universe grows large. Even if spacetime emerges, we still face the question of vacuum energy, because vacuum energy gravitates in general relativity. A constant vacuum energy density acts like a cosmological constant, and it drives accelerated expansion by producing negative pressure. This connects the early universe to a modern mystery, because today's dark energy looks like a tiny vacuum energy. The same concept that animates the emptiest state also seems to steer the fate of the cosmos. Here the problem becomes quantitative and unsettling, because the numbers do not politely disagree. Naive quantum field theory estimates of vacuum energy are enormously larger than what cosmology observes, by many orders of magnitude. The mismatch is the cosmological constant problem, and it is one of the largest known gaps between theory and measurement. It tells us we do not yet understand how vacuum energy couples to gravity, or how it is renormalized in a full theory. The vacuum, in other words, is both a triumph of calculation and a warning that something is missing. This matters for origins because many early universe mechanisms rely on vacuum-like energy, even if they do not call it that. If a field sits in a high-energy state, its potential energy can behave like vacuum energy and dominate the dynamics. That kind of energy can drive rapid expansion, and it can also smooth out irregularities by stretching them away. The same concept that confuses us today may have shaped the first moments. The irony is sharp. The vacuum is central to our models, yet it remains deeply misunderstood. But we must avoid a common narrative trap because a powerful phrase can hide a fragile chain of assumptions. Saying vacuum energy created the universe can compress an entire framework into one misleading sentence. It assumes a field exists, with a potential defined on a spacetime. It assumes dynamical laws that tell the field how to evolve, and it assumes a notion of time in which evolution is defined. The phrase sounds like an explanation, yet it may only be a summary of what we do not know. So what can physics honestly claim at the edge, without turning uncertainty into certainty? It can claim that the earliest accessible era likely involves quantum gravity, because the relevant scales force that conclusion. It can claim that singularities indicate breakdown of classical theory, not necessarily breakdown of nature. It can claim that quantum vacua are physical states, not empty voids. It can claim that quantum fluctuations are real, but they are fluctuations of something, not fluctuations of literal non-existence. It can also claim that our best questions are now sharper, because we know exactly where the old answers stop working. The deeper claim, that nothing is unstable, and therefore must produce something, is more ambiguous than it first sounds. Instability is defined relative to a background and a time parameter, because decay is a time-based concept. A vacuum can be metastable, meaning it can decay to a lower energy state through quantum tunneling. But that story presumes a space-time in which the decay occurs, and a law that defines what lower means. Without a background, even the idea of state becomes difficult to anchor. There is also a confusion between two meanings of nothing, and the difference is where debates often get stuck. One is the lowest energy state within a theory, which is a precise object in mathematics. The other is the absence of the theory's stage and variables, which is harder to even state without contradiction. Physics is good at the first meaning because it can write equations and test consequences. Physics struggles to formalize the second meaning because formalization itself introduces structure. The moment you describe nothing, you have already given it properties. Still, the instability idea points to something important that is not merely semantic. In quantum theory, the vacuum is not a static classical emptiness, but a state with fluctuations and with possible phase transitions. In the early universe, phase transitions could have occurred as symmetries broke, changing the vacuum state and releasing energy into particles. In a cooling cosmos, the vacuum is not a single forever state, but a landscape of possible configurations. Such transitions are central to particle cosmology, because they connect microphysics to cosmic history. As the universe cooled, fields could have shifted from symmetric high-energy states to broken symmetry low-energy states, changing what particles effectively are. These shifts can produce relics like topological defects or generate matter, antimatter asymmetry under the right conditions. They can also set initial conditions for later cosmic evolution, leaving traces in what we can observe. The early universe becomes a record of symmetry, breaking, and the consequences of imperfect transitions. A phase transition is not just a metaphor borrowed from water freezing into ice, although the analogy helps. In a quantum field, the phase is the structure of the vacuum itself, the configuration that minimizes energy. When that minimum changes as temperature and energy scale change, the universe can reorganize its basic degrees of freedom, and the consequences can be dramatic. The vacuum, in this sense, is not emptiness but architecture, and the architecture can be rebuilt as conditions change. But again, these are stories about what happened after a hot, expanding universe already existed, with a notion of time and temperature. They do not yet answer how space-time and the laws themselves began, if they began at all. They answer how a universe, once present, can change its state and generate structure. They are chapters in the middle of the book, not the cover page. The deeper question remains, hovering at the boundary like a silhouette we cannot bring into focus. So we return to the edge, because the edge is where our confidence becomes conditional. At Planck scales, space-time may be foamy, discrete, or emergent, and the word foamy is a placeholder for a real calculation we do not yet possess. Time may not be fundamental, and causality may be approximate, emerging only when geometry becomes smooth. The most honest stance is that our current theories provide boundary markers, not a final origin narrative. What we can say is limited, yet what we can ask is richer than ever. Yet boundary markers are not nothing, and they are not an admission of defeat. They guide what a deeper theory must reproduce, because nature does not let us rewrite the successful parts. Any candidate must reduce to general relativity at low energies, and to quantum field theory in the regimes we test. It must explain why the universe becomes classical and smooth on large scales, and it must connect to observable relics. The edge is not a wall. It is a set of constraints that future explanations must satisfy. This is where the story pivots from origins to initial conditions, because initial conditions are where the universe leaves fingerprints. Even if the universe began in an extreme quantum state, why did it emerge so uniform? Why is space so close to geometrically flat? Why do widely separated regions look so similar in temperature and density? These are not aesthetic preferences, they are measurable facts, and they demand a mechanism. The cosmic microwave background shows uniformity across the sky to 1 part in 100,000, a precision that is almost unsettling. In that faint afterglow, we see a nearly perfect blackbody spectrum, with tiny anisotropies that carry an enormous amount of information. In a simple Big Bang without additional mechanisms, distant regions were never in causal contact early enough to equilibrate. This is the horizon problem, and it is not a philosophical puzzle. It is a mismatch between observed uniformity and naive causal structure. To picture it, imagine 2 points on opposite sides of the sky, separated by a distance light could not have crossed in the early universe. They look as if they agreed on a temperature to exquisite accuracy, even though they could not have exchanged signals in time. The universe appears coordinated in a way that the simplest timeline cannot easily explain. The question is not whether the cosmos expanded, but how it became so evenly prepared for that expansion. There is also the flatness problem, which is about how sensitive cosmic geometry is to initial conditions in the standard expansion. In that framework, any deviation from perfect flatness tends to grow over time, so near flatness today implies extreme fine-tuning early on. There is also the monopole problem in some particle theories, where early phase transitions would overproduce heavy relics we do not see. Each problem is a different face of the same unease. The early universe seems too well arranged. These problems are not proof that the Big Bang is wrong, because the Big Bang model is anchored by multiple independent observations. They are proof that the early story is incomplete, and that the simplest extrapolation is missing a mechanism. They point to a process that sets the initial conditions for the hot Big Bang phase we can test. They also invite a deeper question. Why should the universe's initial state be so special at all? Is the specialness a clue to dynamics, or a clue to something even deeper about what counts as a possible universe? Now, the documentary makes its main transition. If the earliest universe began at the edge of physics, something later must have shaped it into the smooth stage we observe. The next chapter introduces the leading candidate mechanism, and it is both powerful and controversial. It is powerful because it can, in principle, solve several puzzles at once, and it is controversial because it relies on physics in a regime that is difficult to test directly. Enter cosmic inflation, a proposed era of accelerated expansion driven by a vacuum-like energy. Inflation is not a claim about absolute nothing, and it does not pretend to solve the deepest metaphysical version of the origin question. It is a claim about dynamics in the earliest fractions of a second after the Planck boundary, when fields and spacetime already exist in some form. It asks whether a specific kind of energy, with a specific kind of pressure, could have dominated the universe briefly and decisively. Inflation can stretch tiny regions to cosmic scales, making the observable universe originate from a small causally connected patch. It can drive space toward flatness by diluting curvature the way a balloon surface looks flatter as it expands. It can also take quantum fluctuations and expand them into classical density variations, seeding the structure later seen in the CMB and galaxies. In the inflationary picture, the faint mottling in the microwave sky is not noise. It is the fossil imprint of quantum uncertainty, magnified to astronomical size. The idea is audacious because it uses the vacuum-like behavior of a field as a kind of engine, and it asks that engine to run in an extreme regime. It also makes a testable promise because it predicts a particular pattern of primordial perturbations. That promise is why inflation moved from speculation into a central working hypothesis for many cosmologists. The sky becomes a laboratory, not because we can rerun the experiment, but because the universe preserved the results. But inflation also inherits the chapter's core tension, and it cannot escape it. It relies on quantum fields and vacuum energy, concepts that are not nothing, and it pushes them into regimes we cannot reproduce directly. It is a bridge between the unknown Planck era and the tested hot Big Bang, and bridges must be checked from both sides. If the bridge is real, it should leave signatures that survive billions of years of cosmic evolution. So Chapter 3 ends with a sharpened mystery rather than a resolved origin, because the honest ending is not a tidy one. Nothing, in physics, is rarely absolute absence, even when the word is used casually. It is often a quantum vacuum, a lowest energy state with structure and fluctuations. The Planck epoch marks where even that language may fail, because spacetime itself may be emergent. The next question is not only what happened, but what it would even mean to say happened at the edge. Next, we ask whether inflation is the missing mechanism that turns an extreme beginning into a universe that looks simple, smooth, and strangely uniform. We follow its predictions into the sky, because the only way past the edge is evidence. Imagine a time when there wasn't even time, then picture a universe that suddenly outran itself. In that strange opening, our usual intuitions fail, because cause and effect depend on a clock that may not yet exist. Inflation enters as a proposed answer to why the early cosmos looks prepared, coordinated, and strangely smooth, almost as if it had time to settle before time had truly begun. Chapter 3 ended at the Planck boundary, where spacetime may be emergent and our equations lose authority. That boundary is not a wall we can see, but a limit we infer from dimensional analysis and the breakdown of known physics. At roughly 10 around 43 seconds, quantum fluctuations of geometry become so violent that classical spacetime may not be the right language. In that regime, even the idea of a definite distance can blur because the metric itself is part of the quantum uncertainty. Inflation does not claim to describe absolute nothing, because it assumes fields and a spacetime description already exist, even if that spacetime is only an effective stage. It begins after the moment when we can speak, however cautiously, about expansion and energy density. That modesty is not a weakness in the idea, because it marks the boundary between physics we can model and metaphysics we can only gesture toward. This matters for tone as much as for physics, because the word beginning can hide several different questions. Inflation is not the origin of existence in the philosophical sense, and it does not pretend to be. It is a dynamical episode placed after some prehistory we cannot yet calculate, where before might be a misleading word. The proposal is narrower, but still radical. Given some early patch of space-time with the right energy conditions, the universe can expand in a way that reshapes what later observers call the beginning. Enter cosmic inflation, a proposed era of accelerated expansion driven by a vacuum-like energy. Inflation is a brief era of accelerated expansion, often placed around 10 to 36 to 10 32 seconds after the start of the hot Big Bang phase. Those numbers are not measured directly, but inferred from how much expansion is needed to solve the puzzles that otherwise remain. The core idea is simple in form and extreme in consequence, because the geometry responds to what dominates the energy budget. In general relativity, pressure gravitates, and negative pressure can drive repulsive gravity on cosmic scales. This is one of the theory's least intuitive features, because we are used to pressure pushing outward, not changing the curvature of spacetime itself. Yet in Einstein's equations, energy density and pressure both contribute to gravity's source. When pressure is sufficiently negative, the combination that governs acceleration becomes negative, and the expansion accelerates. A useful way to say it in plain language is that the universe does not only weigh energy, it also weighs how that energy pushes back. For ordinary matter, pressure is small compared with energy density, and gravity pulls the expansion towards slowing. For radiation, pressure is positive and substantial, and it still slows expansion because the pressure term adds to gravity's attractive effect. A vacuum-like component is different, because its pressure is negative and nearly equal in magnitude to its energy density. A field trapped in a high-energy state can behave like that, with nearly constant energy density as space expands. In ordinary matter or radiation, energy density dilutes as the universe grows, because particles spread out and wavelengths stretch. A vacuum-like component is different. It does not thin out in the same way, so its gravitational effect persists. This is the inflaton idea, a placeholder name for whatever field or mechanism produced that vacuum-like state. The inflaton is often pictured as a scalar field, meaning it has a value at every point in space but no preferred direction. Scalar fields are not fantasy objects because the Higgs field is a confirmed example in particle physics. Still, the inflaton is not identified with certainty, and the name is a sign of humility. It tells us we are describing behavior first, then asking what fundamental entity could produce it. During inflation, the scale factor grows almost exponentially, meaning distances double again and again in tiny fractions of a second. Exponential growth is not merely fast because it compounds, and the compounding quickly becomes overwhelming. Cosmologists often count this growth in e-folds, where each e-fold multiplies distances by e. Roughly 50 to 60 e-folds is enough to turn a subatomic patch into something that can contain our entire observable sky. A region once smaller than an atom's nucleus can become larger than the observable universe we see today. That growth is why inflation is sometimes called a cosmic growth spurt, though the phrase hides the mathematical severity. The expansion is so rapid that what was once tightly connected becomes stretched beyond any chance of later communication. In that sense, inflation is not just expansion, it is an editing of what can ever be causally compared. For visuals, imagine a grid drawn on a rubber sheet. Then imagine the sheet swelling so quickly that the grid lines race apart. Galaxies are not yet there, and even particles may not have their later meaning, but the geometry itself is stretching. The expansion is not an explosion into empty space, because there is no outside in the model. Space is what is growing, and the distances between moving points increase because the metric changes. Historically, inflation emerged in the late 1970s and early 1980s, when cosmologists confronted a set of puzzles that seemed unrelated. The horizon problem, the flatness problem, and the relic problem looked like separate embarrassments for the simplest Big Bang picture. Researchers such as Alan Guth proposed that a phase transition in the early universe could drive a period of accelerated expansion. That first proposal had a graceful exit problem, because ending inflation smoothly is as difficult as starting it. Later refinements, new inflation, chaotic inflation, and slow-roll models shifted the mechanism while keeping the core geometric effect. The history matters, because inflation was not born as a single polished theory, but as a response to stubborn data and uncomfortable coincidences. Over time, it became less like a single machine and more like a family of engines. Each engine aims to produce the same broad outcome, a universe that looks older, smoother, and flatter than naive expansion would suggest. The first puzzle inflation targets is the horizon problem, which comes directly from the CMB's uniform temperature. The CMB is the afterglow of the time when the universe cooled enough for electrons and protons to combine into neutral atoms. Before that moment, photons scattered constantly, and the universe was an opaque plasma. After recombination, photons streamed freely, carrying a snapshot of conditions across the sky. When satellites map the CMB, they find a temperature of about 2.7 Kelvin, with variations at the level of tens of microkelvin. The uniformity is startling, because it is uniform across regions that, in a non-inflationary picture, could not have exchanged light or heat. In the standard hot Big Bang without inflation, widely separated CMB regions were never in causal contact before recombination. They should not share the same temperature to 1 part in 100,000. The word horizon here is not a physical edge, but a causal limit set by the finite speed of light and the universe's expansion history. If two regions have never been able to send signals between them, they cannot equilibrate by ordinary processes. Without inflation, the sky appears to be stitched from many causally isolated patches, each with no reason to match its neighbours so precisely. The puzzle is not that the CMB is smooth, but that it is smooth everywhere at once. Inflation changes the causal story by shrinking the pre-inflation patch that becomes our observable universe. Before the growth spurt, that patch can be small enough for light and interactions to equilibrate it. In that earlier phase, the horizon encompasses the whole region that will later become our cosmic view. After the growth spurt, the same patch is stretched so far that it looks like many disconnected regions today. Uniformity then becomes a memory of earlier contact, not a coincidence across disconnected skies. The CMB's smoothness becomes a fossil of a time when the observable universe was a single neighbourhood. Inflation does not remove horizons, but it rewrites when the relevant horizon was set. The causal structure is rearranged, so the uniformity is no longer miraculous, just inherited. Visually, you can picture a tiny, warm droplet of plasma that has time to settle to an even temperature. Then the droplet is pulled outward like taffy, becoming a vast sheet that later observers mistake for separate pieces. The temperature match remains, because it was established when the region was compact. What looks like coordination across the sky is, in this story, the stretched imprint of an earlier unity. The second puzzle is flatness, the near-critical geometry inferred from CMB acoustic peaks and large-scale structure. In cosmology, flat does not mean empty, and it does not mean two-dimensional. It means the spatial geometry is very close to Euclidean, so parallel lines behave as expected, and triangles add to 180 degrees within measurement limits. The key quantity is the density parameter, often written as O, which compares the actual energy density to the critical density needed for a flat geometry. In standard expansion, any slight departure from perfect flatness tends to grow over time. That is a mathematical statement about how the curvature term evolves relative to matter and radiation as the scale factor increases. If O was even a tiny bit different from 1 in the early universe, the difference would amplify, and today's universe would be dramatically curved. That makes today's near flatness imply an implausibly fine-tuned early value, tuned to many decimal places. Inflation drives the universe toward flatness by diluting curvature the way a balloon's surface looks flatter as it expands. On a small patch of a large sphere, curvature becomes harder to detect because the radius of curvature grows. In the equations, the curvature term becomes negligible compared with the rapidly growing scale factor. Flatness becomes an attractor behaviour rather than a tuned initial condition, and the universe is pushed toward O very close to 1. The third puzzle is the relic problem, often framed around magnetic monopoles predicted by some grand unified theories. In certain high-energy models, early phase transitions can produce heavy, stable relics, including monopoles and other topological defects. These objects would be rare in ordinary conditions, but the early universe's temperatures could make them plentiful. Standard expansion would leave too many behind, and their mass would dominate the universe in ways we do not observe. We do not observe a universe clogged with monopoles or similar defects at the predicted level. Their absence is not a minor detail, because it constrains the kinds of symmetry breaking that could have occurred. Inflation solves this by dilution, not by forbidding relics from forming. If monopoles were produced before inflation, the exponential expansion spreads them so thin that essentially none remain in our observable volume. The same logic can suppress other unwanted relics, depending on when they form. If defects form after inflation, dilution cannot help, so timing matters. That timing becomes part of the model-building challenge, because inflation must fit not only geometry but also particle physics history. Even so, the basic point is powerful. An enormous expansion can turn too many into almost none, simply by stretching space. These successes explain why inflation became a leading bridge between the unknown Planck-era boundary and the tested hot Big Bang. Yet the bridge must do more than smooth and dilute, because the universe is not perfectly uniform. The CMB contains tiny anisotropies, and galaxies exist because small differences grew. A universe that is too smooth remains a fog forever, with no stars, no planets, and no observers to ask how it began. Inflation offers a mechanism for those differences, and it is the chapter's central twist. Quantum fields cannot be perfectly still, even in their lowest energy states. This is not a statement about measurement devices, but about the structure of quantum theory itself. The uncertainty principle implies that field values and their conjugate momenta cannot both be exactly fixed, so there is always residual jitter. That jitter is not a metaphor, because it can be computed as fluctuations around a vacuum state. In a rapidly expanding background, the vacuum itself is subtle, because what counts as empty depends on the observer's notion of time. Inflation provides a near de Sitter spacetime, where the expansion rate is almost constant. In that setting, quantum modes are continually stretched, and the vacuum fluctuations are promoted into real, persistent patterns. During inflation, quantum fluctuations in the inflaton and in spacetime itself are stretched from microscopic wavelengths to astronomical scales. In ordinary settings, such fluctuations remain microscopic and average out. Inflation changes the bookkeeping, because it takes tiny ripples and drags them across the sky. The expansion acts like a magnifying lens, though the lens is the universe's own geometry. A fluctuation that begins as quantum noise becomes a classical-looking perturbation once its wavelength is stretched beyond the horizon during inflation. Horizon here refers to the Hubble radius, the scale beyond which causal processes cannot keep up with expansion. Outside that scale, the mode stops oscillating in the usual way, and its amplitude effectively freezes. The perturbation becomes a record, stored in the curvature of space and the distribution of energy. Later, as expansion slows and the horizon grows, those modes re-enter and become real density variations. Regions that are slightly denser pull in more matter, and regions that are slightly less dense fall behind. Gravity amplifies the contrast, slowly at first, then more dramatically as matter dominates over radiation. This is the proposed pipeline from quantum uncertainty to cosmic structure, a chain that links the smallest scales to the largest. The CMB's mottled temperature map then becomes a statistical imprint of primordial curvature perturbations. The hot and cold spots are not random stains, but the projection of a three-dimensional pattern onto the celestial sphere. Galaxies and clusters become the late-time gravitational amplification of those early seeds. The cosmic web, filaments, nodes, and voids, can be traced back to a nearly featureless spectrum of tiny initial differences. For visuals, imagine the CMB map as a soft, speckled globe, then dissolve into a simulation where those speckles thicken into filaments. The camera can drift through a dark matter scaffold where luminous galaxies appear like dew on invisible threads. As the view pulls back, voids open like black lakes between shining strands, and clusters burn like embers at the intersections. The narration can linger on the idea that the pattern began as uncertainty, not as design. The inflationary perturbations are predicted to be nearly scale invariant, meaning similar power across a wide range of wavelengths. In plain language, the universe looks statistically similar whether you zoom in or out, at least across many scales. exact scale invariance would be too perfect, and real models predict a slight tilt. That tilt carries information about how inflation proceeded and how quickly the inflatant's energy changed. They are also predicted to be adiabatic, meaning matter and radiation fluctuate together in a correlated way. That correlation matters because it determines the phase of acoustic oscillations in the early plasma, which later show up as peaks in the CMB power spectrum. They are predicted to be nearly Gaussian, meaning the fluctuations behave like a random field with small non-Gaussian corrections. Gaussianity is not a philosophical preference, but a consequence of simple quantum fluctuations in a weakly interacting field. These are not aesthetic claims, because they translate into measurable statistics in the CMB and in galaxy surveys. The power spectrum's tilt is summarized by the scalar spectral index, NLS, which would be exactly 1 for perfect scale invariance. Observations find NIS slightly less than 1, consistent with many slow-roll inflation models. That slightly less is a small deviation, but it's a loud clue, because it rules out some alternatives. The phrase slow roll refers to how the inflatant field moves along its potential energy landscape. The potential is like a contour map, with hills, valleys and plateaus that determine how the field evolves. If the potential is flat enough, the field rolls slowly, and the vacuum-like energy dominates long enough to inflate. If the potential is too steep, the field falls quickly, inflation ends too soon, and the universe does not get smoothed. In more technical terms, slow roll means the field's kinetic energy stays small compared with its potential energy. That condition keeps the expansion rate nearly constant, which is what makes the perturbation spectrum close to scale invariant. It also means inflation can last long enough to erase curvature and unwanted relics. The elegance is that one dynamical condition, slow evolution on a flat potential, can explain several observational regularities at once. The same potential shape sets the amplitude and tilt of the perturbations, linking microphysics to sky maps. The amplitude tells us how strong the initial seeds were, which later affects how quickly structure forms. The tilt tells us how the expansion rate changed during inflation, because different scales exit the horizon at different times. In this way, the CMB becomes a laboratory for energies far beyond what particle accelerators can reach. Inflation also predicts tensor perturbations, primordial gravitational waves produced by quantum fluctuations of spacetime. These are not waves traveling through space like sound through air, but ripples in spacetime itself. Their existence is a generic prediction of inflationary expansion, though the amplitude depends strongly on the energy scale. If inflation occurred at very high energies, the tensor signal could be within reach of experiments. These waves would leave a distinct imprint in CMB polarization, particularly a curl-like B-mode pattern. Polarization is a subtle alignment in the CMB's light, produced when photons scatter off electrons in the presence of quadrupole temperature anisotropies. Scalar perturbations mainly produce E-modes, which have a gradient-like pattern. Tensor perturbations can produce B-modes, which have a swirling pattern that cannot be made from gradients alone. Detecting primordial B-modes would be strong evidence for inflation's high-energy dynamics. It would not identify the inflaton by name, but it would reveal the energy scale and confirm that spacetime itself was fluctuating quantum mechanically. It would be a measurement of gravity in a regime we otherwise only imagine. That is why B-modes have become one of the most sought-after signals in observational cosmology. But B-modes are difficult, because foreground dust and astrophysical signals can mimic or obscure the pattern. Our galaxy emits polarized radiation, and interstellar dust grains align with magnetic fields, producing polarized light that can look deceptively similar. Experiments therefore chase a faint signal through careful multi-frequency measurements and cross-checks. They separate components by how the signal changes with frequency, and by comparing different patches of sky. So far, the result is upper limits on the tensor-to-scalar ratio, which already rule out some simple inflation models. The tensor-to-scalar ratio, often written R, compares the strength of gravitational wave perturbations to density perturbations. Large field models that predict high R values have been squeezed by data. The absence of a detection is not a failure, but a constraint that shapes what inflation can be. Inflation is therefore not a single theory, but a framework with many possible potentials, fields, and mechanisms. Different models predict different values for NIS, for the tensor amplitude, and for non-Gaussianity. Some models involve one field, others involve multiple fields, and some modify gravity itself while keeping the inflationary expansion. The data acts like a filter, narrowing the space of viable models without yet selecting a unique one. This is where the mysterious tone returns, because inflation explains a lot while leaving deep questions open. What exactly is the inflaton, and why should such a field exist in fundamental physics? Is it related to known fields like the Higgs, or is it something entirely new? If it is new, why does it couple to ordinary matter in the way reheating requires, and why does its potential have the right shape? Even if an inflaton exists, inflation must end, and ending is as important as beginning. A universe that inflates forever in our region would become empty and cold, because matter and radiation would be diluted away. The vacuum-like energy must convert into particles and radiation, or the universe would remain cold and empty despite its vast size. That conversion is called reheating, and it is where inflation hands the story back to the hot Big Bang. Reheating is not a single event, but a dynamical process where the inflaton's energy decays into a thermal bath. In many models, the inflaton begins to oscillate around the minimum of its potential, behaving like a condensate of inflaton quanta. Those oscillations can transfer energy to other fields through couplings, producing particles in a burst. The process can include non-perturbative effects, sometimes called preheating, where particle production is explosive rather than gradual. Visually, reheating can be framed as a universe that goes from silent expansion to sudden chatter. The smooth, vacuum-dominated stage gives way to a storm of interactions, where fields dump energy into a hot plasma. The darkness fills with radiation, and the concept of temperature becomes meaningful again. It is the moment the universe regains an inventory, species, collisions, and a thermal history we can calculate. The details affect the temperature reached, the production of relics, and the matching between inflationary scales and present observations. The reheating temperature influences which particle species are produced abundantly, and whether certain symmetries are restored and broken again. It also affects how many E-folds of inflation are required, because the later expansion history depends on the equation of state during reheating. In that way, uncertainty in reheating becomes uncertainty in how we map CMB scales to inflation's timeline. Because reheating is uncertain, it introduces a gap between the clean inflationary picture and the well-tested later universe. That gap is not fatal, but it is a reminder that early universe cosmology often relies on effective descriptions. We infer the beginning of the hot phase, but we do not directly observe the handoff. The handoff is like a cut in a film, where the scene changes, and we reconstruct what happened between frames. Another uncertainty is initial conditions for inflation itself. Inflation is often presented as a solution to fine-tuning, yet it may require its own special starting patch. The patch must be smooth enough and dominated by the right energy to begin accelerating rather than collapsing or fragmenting. If gradients or inhomogeneities are too large, they can prevent inflation from starting, or they can end it prematurely. Some models claim inflation is an attractor, meaning many initial conditions flow toward inflationary behavior. In these models, expansion damps away certain kinds of irregularity, and the inflating solution becomes stable. Other analyses argue that the required conditions are still rare in a broader space of possibilities. The debate matters because it touches the central question, not just the math, and it forces us to ask what natural means in a universe with only one realized history. If inflation needs a special start, then it may not answer why the universe was prepared, only how preparation is amplified. It can move the apparent fine-tuning earlier into the conditions that allow inflation to begin. The documentary's tension sharpens here, because the word nothing is still waiting in the background. Inflation can explain why a patch becomes enormous, but it does not automatically explain why that patch existed, or why it had the right properties. There is also the possibility of eternal inflation, where inflation ends in some regions but continues in others. Quantum fluctuations can keep parts of the inflating field high enough that expansion outruns decay. In that picture, inflation is not a single event in the past, but a process that never completely stops. The universe becomes a kind of fractal, with inflating regions spawning non-inflating pockets. Eternal inflation leads naturally to a multiverse-like structure, with bubble regions that reheat into hot Big Bang universes. Different bubbles could realize different low-energy physics, depending on how fields settle into vacuum states. The idea is not that anything is possible, but that many outcomes might be realized somewhere in the larger inflating spacetime. This can make inflation feel both explanatory and unsettling, because it changes what counts as a prediction. If many outcomes occur, then the question becomes why we observe this particular set of parameters. Some researchers appeal to selection effects, because observers can only arise in certain conditions. Others argue that without a clear measure and testable consequences, the multiverse risks sliding from physics into uncheckable narrative. The discomfort is methodological as much as emotional, because science depends on what can be compared to data. Inflation therefore sits in a delicate position between evidence and extrapolation. Its core predictions about scalar perturbations match the CMB remarkably well, including near Gaussianity and the observed tilt. The acoustic peaks line up with a story of adiabatic initial conditions and coherent oscillations in the early plasma, yet the mechanism's deeper identity remains unknown, and its most dramatic signature, primordial B-modes, remains undetected. That mixed status is not a weakness of the documentary, but a key beat in the story. Inflation is powerful because it compresses several puzzles into one dynamical episode. Inflation is fragile because it depends on high-energy physics we cannot probe directly, and because it can be made to fit many outcomes. The framework can be flexible, and flexibility is both a strength and a warning. Still, inflation's central achievement is conceptual, because it links quantum fluctuations to the largest structures in the universe. It turns the CMB anisotropies into a fossil record of quantum randomness stretched to cosmic size. The universe's first texture becomes a measurable statistical field, not a poetic metaphor. In a sense, inflation turns the sky into a graph of the early universe's quantum state. To make that link precise, cosmologists track how perturbations evolve from inflation to recombination to today's galaxies. They compute transfer functions that describe how different scales grow or are suppressed, depending on whether they enter the horizon during radiation domination or matter domination. They include the effects of baryons, which couple to photons early on and create acoustic features. They compare predictions to the CMB power spectrum to baryon acoustic oscillations and to the clustering of galaxies. The match is not perfect in every detail, but it is coherent across multiple datasets. The same initial perturbations that explain CMB peaks also seed the cosmic web seen in surveys. Large-scale structure measurements, weak gravitational lensing, and galaxy clustering all point back to a consistent primordial spectrum. This coherence is why inflation remains the leading candidate for the universe's early smoothing and seeding mechanism. Yet the documentary's central question is not only about smoothness and seeds, it is about beginnings, and about what nothing could mean when time itself is part of the story. Inflation assumes a stage where fields exist and evolve, even if that stage is exotic and early. It assumes a semi-classical description where space-time is smooth enough to talk about expansion, even if that smoothness is itself a product of earlier physics. So inflation may not answer why there is something rather than nothing, because it begins after something already exists. It may instead answer a narrower but crucial question. Given an early quantum gravity boundary we cannot yet describe, how did the universe become the hot, nearly uniform, nearly flat cosmos our evidence demands? That is not the ultimate why, but it is a how that can be tested against the sky. This is why inflation is framed as a bridge, not as the ultimate origin. It connects the unknown edge of physics to the parts of cosmic history we can test. It explains why the universe looks older than it should, smoother than it should, and emptier of relics than some theories would predict. It also explains why the universe is not perfectly smooth, because the same mechanism that smooths also seeds. Now we pivot to what inflation leaves unfinished because every bridge ends on another shore. After reheating, the universe is filled with particles, radiation, and fields that follow the standard hot Big Bang evolution. The temperature is high, interactions are frequent, and the contents of the universe can be described by particle species in a thermal bath. But the inventory of those particles, and the forces between them, still needs explanation. We also face the asymmetry problem, because matter dominates over antimatter in the observable universe. If the early universe produced matter and antimatter equally, they should annihilate back into radiation, leaving little behind. The fact that anything remains, atoms, stars, and the chemistry of life, implies a tiny bias in the early accounting. Something in the early dynamics must have tilted the balance. Inflation does not automatically create that bias, though it can set conditions under which it happens. By diluting pre-existing particles, inflation can erase earlier asymmetries, making the post-inflation universe depend strongly on what happens during and after reheating. The asymmetry likely involves particle physics beyond the simplest standard model, and it may involve out-of-equilibrium processes after reheating. The next chapter follows that trail, from fields to particles, and from symmetry to the imbalance that lets anything exist. Inflation, then, is both an answer and a deferral. It answers how quantum noise can become cosmic structure, and how early conditions can be smoothed and flattened. It defers the deeper question of what started inflation, and whether that start is just another way of naming the unknown. It gives us a working narrative that fits the data while leaving the first cause in shadow. The mysterious edge remains, but it is now constrained by evidence. The CMB is not only a glow, but a set of numbers that any origin story must match. Those numbers include the peak structure, the tilt, the amplitude, and the tight limits on non-Gaussianity. Inflation is one of the few ideas that can meet those numbers while keeping the narrative tied to physics. We end this chapter with the hook still alive but sharpened by a new possibility. Imagine a time when there wasn't even time, then imagine quantum fluctuations becoming galaxies. If inflation shaped reality's first large-scale features, the next question is what filled that reality with the specific matter and forces we know? The universe's geometry may have been prepared, but its contents still need a recipe. Next, we ask how the universe acquired its particle content, and why it contains more matter than antimatter. We follow the trail from reheating into the era where particle physics writes the universe's inventory, and where existence becomes a measurable imbalance. Inflation gave the universe a smooth stage and a spectrum of tiny seeds. It stretched space so violently that any earlier wrinkles were ironed nearly flat, yet quantum fluctuation survived, promoted into cosmic-sized variations. Those fluctuations were not added by hand, because quantum fields cannot be perfectly still, even in their lowest energy state. Now the central question returns in a harsher form. If nothing existed before the Big Bang, why did anything remain after it began? Visually imagine a dark, almost featureless expanse, then a sudden swelling like a balloon in fast motion. The camera glides over a field that looks empty, but it is not truly empty. In modern cosmology, empty can still mean energy stored in a field, and that stored energy can dominate everything. The darkness is not a void in the everyday sense. Think of it as a taut, silent reservoir ready to release its contents. Reheating is the handoff from inflation's vacuum-like energy to the hot Big Bang. It is the moment a nearly empty, rapidly expanding cosmos becomes a crowded thermal bath again. The inflaton's stored energy must convert into particles, or expansion leaves a cold, dilute universe with no chemistry. In other words, reheating is where the story regains substance, where fields begin to look like matter and radiation. During inflation, the energy density is almost constant, so the universe behaves as if it is pushed by a kind of negative pressure. That pressure is not a metaphor, because it is encoded in the stress, energy tensor that drives Einstein's equations. In the Friedmann equations, pressure gravitates too, so a sufficiently negative pressure makes expansion accelerate rather than slow. When inflation ends, the equation of state changes, and the universe must find a new way to carry its energy forward. Reheating is that bridge, and it is also a blind spot in our knowledge. We infer it indirectly by demanding that the later universe becomes hot enough for nucleosynthesis and the known thermal history. Yet the microphysics, what the inflaton couples to, how efficiently it decays, and how quickly equilibrium is restored, remains model-dependent. Even the duration matters, because a prolonged reheating phase changes how much the universe expands before it becomes truly hot. In many models, the inflaton oscillates around its potential minimum, behaving like a coherent condensate. Those oscillations dump energy into other fields through couplings that may be weak, unknown, or highly model-dependent. Particle production can be perturbative and gradual, or explosive during preheating, when resonance amplifies certain modes. The difference is not cosmetic. One path drips energy slowly, while the other can flood the universe in a burst. To picture it, think of a field vibrating everywhere in space at once, like a drumhead spanning the cosmos. Each oscillation is not just motion, it is energy available to create quanta of other fields. In perturbative reheating, the inflaton decays like a particle with a lifetime, producing daughter particles in a steady trickle. Those daughters then scatter, split and cascade, an early universe version of a particle shower, building complexity from a simple source. Preheating is more dramatic, and it can be almost cinematic in its speed. Resonant effects can pump energy into specific momentum modes, like a child pushing a swing at just the right frequency. Occupation numbers in those modes can become enormous, and the universe can briefly behave more like a classical wave system than a dilute gas. The visuals here can show rippling bands of brightness, standing waves that suddenly fracture into a storm of quanta. The details matter because temperature is not automatic. A temperature is a statement about a distribution, and a distribution requires interactions that mix and randomize energies. Reheating therefore includes thermalization, when scattering and decay processes convert an initially structured set of excitations into an approximately thermal plasma. Until that happens, the universe may be energetic but not yet thermal, hot in total, yet uneven in how that heat is shared. Reheating sets an initial temperature for the standard Big Bang trajectory. That temperature determines which particle species are populated, which symmetries are restored, and which relics are created or erased. It also affects how we map CMB scales back to inflation, because the post-inflation equation of state changes the expansion history. In practice, a different reheating temperature shifts the timeline, altering when key processes freeze out. Even the phrase initial temperature hides a subtlety. Different sectors might not share the same temperature at first, especially if the inflaton couples more strongly to some fields than others. A hidden sector could be reheated weakly, leaving it cooler, darker, and harder to detect later. That possibility is one reason cosmologists treat reheating as both a conclusion to inflation and a doorway to unknown physics. From a visual standpoint, reheating is where the film changes texture. The emptiness becomes grainy, then bright, as particle creation fills space with a dense fog of interactions. The palette shifts from black to incandescent, like a furnace being opened, except the furnace is everywhere. You can show sparks becoming a continuous glare, an ocean of collisions where no particle keeps its identity for long. Once reheating completes, the universe is hot, dense, and close to thermal equilibrium. Energy is mostly radiation, and the expansion is decelerating again under ordinary gravity. The story becomes particle physics in a cosmic box, where temperature acts like a dial that changes what the vacuum looks like. That dial is not arbitrary, because temperature sets which degrees of freedom are active and which are effectively frozen out. In this radiation-dominated era, the scale factor grows more slowly than during inflation, and horizons behave differently. Regions that were once driven apart faster than light could communicate now begin to re-enter causal contact. The universe is still expanding, but it is no longer doing so in the runaway way inflation imposed. The camera can linger on a subtle change in motion, an expansion that still wins but no longer overwhelms everything. At extreme temperatures, familiar distinctions between particles blur into a plasma of fields. Interactions are so frequent that individual particles are short-lived excitations, constantly created and destroyed. The early universe is not a quiet inventory of objects, but a statistical system governed by symmetries. In this regime, conservation laws and selection rules feel like the true characters because they decide what reactions are allowed. In quantum field theory, particles are excitations of underlying fields, and at high temperature the vacuum is replaced by a thermal state. Masses and couplings can receive thermal corrections, shifting effective potentials and changing which configurations are stable. In plain terms, heat reshapes the landscape that fields roll on. A field that prefers one configuration at low temperature can be held in a different one by the pressure of the thermal bath. As the universe cools, it passes through phase transitions that reshape the rules. These are not optional events added for drama, because they are predicted by quantum field theory at high temperature. The vacuum state changes, and what counts as mass, charge, and force can change with it. The mystery is that the vacuum, which sounds like nothing, behaves like something with phases and properties. Phase transitions in the early universe can be smooth crossovers or sharp first-order events with latent heat. In a first-order transition, bubbles of a new phase nucleate and expand, and their walls can sweep through the plasma like moving boundaries. In a crossover, the change is gentler, but it still alters the effective degrees of freedom. Either way, the expansion rate feels the change, because pressure and energy density respond differently across the transition. Historically, our confidence in these transitions grew alongside the development of gauge theories and the Standard Model. In the 1970s, the unification of electromagnetic and weak interactions gave a concrete framework for electroweak symmetry. Later, lattice gauge theory made the QCD transition a computational target, connecting cosmic history to numerical experiments. The early universe became not just a story, but a testbed where particle theory could be forced to answer to the sky. One key regime is the quark, gluon plasma, where quarks and gluons are not confined inside hadrons. At temperatures above the QCD confinement scale, color charges roam freely in a strongly interacting soup. As expansion cools the plasma, confinement turns free quarks into bound states, like protons and neutrons. This is the moment when matter begins to look like the matter we recognize, because stable baryons become meaningful objects. To visualize the quark, gluon plasma, imagine matter so hot that nuclei cannot exist, and even protons dissolve. The medium is opaque and viscous, a liquid-like state where gluons constantly exchange color charge. In heavy ion colliders, we create tiny droplets of this plasma, and they flow like a near-perfect fluid. The documentary can echo those experiments, brief flashes in a detector, then expand them outward into a universe-sized version. The early universe's quark, gluon plasma, is not a droplet, but an all-encompassing ocean. Quarks are not little balls moving in space. They are quantum excitations whose identities are constantly reshuffled by strong interactions. The distinction between inside and outside a hadron has not yet formed. If you could see it, you would not see particles so much as a shimmering, restless medium, where color is everywhere but never isolated. As the temperature falls toward roughly 100 to a few hundred mega electron volts, the strong force changes character. Confinement emerges, and quarks become locked into color-neutral combinations. The result is a sudden simplification of the particle inventory, as hadrons become the relevant degrees of freedom. There is also a thermodynamic signature here, an abrupt change in how many effective degrees of freedom contribute to the energy density. This transition is not merely a switch from one particle list to another. It changes how pressure and energy density behave, which feeds back into the expansion rate. It also sets the stage for later nuclear reactions, because stable baryons must exist before nuclei can form. In the visuals, the chaotic ocean can appear to granulate, as if a continuous fluid condenses into discrete persistent islands. In cosmology, the expansion rate depends on the total energy density, but also on how that energy responds to expansion. When degrees of freedom drop out of equilibrium or become massive, the relationship between temperature and scale factor shifts. That shift affects timing, and timing matters for every freeze-out and every relic abundance. The universe is a clock built from reactions, and every transition slightly retunes its ticking. Another major transition is electroweak symmetry breaking, when the Higgs field takes on a non-zero value. Above the electroweak scale, electromagnetic and weak interactions are unified in a single electroweak force. As the universe cools, the symmetry breaks, and the W and Z bosons become massive. Historically, this picture gained credibility after the Higgs mechanism was formulated in the 1960s, then confirmed decades later at the LHC. Here the visuals can become more abstract, because the Higgs field is not a substance you can point to. Picture a field filling all space, like a background color that suddenly deepens, and with that deepening the rules of motion change. Particles that once moved as if massless now feel resistance, as if the medium itself has thickened. The camera might show trajectories bending, not from collisions but from a new property of space itself. At high temperature, the Higgs potential is modified by thermal effects, and the symmetric state is favored. As the universe cools, the effective potential tilts, and the broken symmetry state becomes the minimum. In plain language, the universe finds a new resting configuration, and that choice gives masses to certain particles. The change is global, but it is also local in consequence. Every interaction now plays by updated rules. This is where forces differentiate as temperature falls, and where the universe's low-energy rules crystallize. The photon remains massless, leaving long-range electromagnetism. The weak force becomes short-range, not because it weakens, but because its carriers gain mass. What looks like a subtle mathematical shift becomes a practical boundary for the future, because long-range forces build structure, while short-range forces govern transformations. The short range of the weak force is a consequence of Yukawa suppression in the propagator, which is a technical way of saying massive carriers do not mediate long-distance effects efficiently. The photon, being massless, can carry electromagnetic influence across astronomical distances. This contrast will later shape chemistry, stars, and the very possibility of stable atoms. In the background, it also shapes how neutrinos decouple, because weak interactions become less effective as the universe cools. These transitions connect back to the documentary's theme about nothing and vacuum structure. A vacuum is not empty in modern physics, because it is a state with symmetry and energy. When the vacuum changes phase, the universe can release latent energy and create new particle populations. The ground state is therefore not a blank floor but a patterned surface, one that can crack, shift, and settle into new forms. In older intuitions, nothing meant absence, a blank stage where events happen. In quantum field theory, the stage itself is active, defined by expectation values, fluctuations, and symmetry constraints. The vacuum is a kind of material, not in the everyday sense, but in the sense that it has properties with measurable consequences. The question becomes unsettling. If the vacuum has structure, then what does it mean to say the universe began from nothing? Yet a deeper tension remains, because a hot universe naturally makes matter and antimatter in nearly equal amounts. If symmetry were perfect, every quark would meet an antiquark and annihilate into photons. The universe would end as radiation with no atoms, no stars, and no observers. The mystery is not why annihilation happens, but why it did not finish the job. This is not a philosophical worry, but a quantitative one. In thermal equilibrium at high temperature, particle-antiparticle pairs are produced and destroyed continually, and their number densities track the temperature. As the universe cools below particle masses, annihilation dominates, and without an asymmetry, the survivors would be exponentially suppressed. In that limit, the leftover baryon density would be so tiny that galaxies would struggle to gather enough raw material. The fact that anything survived implies a tiny imbalance in the earlier counting. The asymmetry is small, roughly 1 extra baryon per billion photons, but it decides everything. The chapter's stakes sharpen here, because survival requires a violation of naive symmetry. You can visualize the annihilation as a bright universal flare, followed by a quiet residue, like embers that persist after a fire consumes almost all its fuel. That 1 in a billion is not a poetic number, because it is inferred from independent measurements. The baryon density extracted from the cosmic microwave background matches the baryon density required by primordial deuterium and helium abundances. Two very different cosmic records agree on the same tiny excess. When independent lines of evidence converge like this, the universe is telling us the imbalance is real, not an artifact of one method. Baryogenesis is the name for mechanisms that generate a net baryon number. Leptogenesis is a related route that first creates a lepton asymmetry, later converted into baryons by electroweak processes. Both ideas answer the same question: why the universe did not annihilate itself back into light. They also turn the early universe into a proving ground, because the asymmetry is a fossil that cannot be forged later. The language here is careful for a reason. We are not merely asking how to make matter, because matter and antimatter are made easily in a hot plasma. We are asking how to bias the bookkeeping so that, after annihilation's finish, a residue remains, small but not zero. That residue is the difference between a universe with chemistry and a universe with only cooling radiation. The required ingredients were stated by Sakharov, and they remain the checklist. First, baryon number must be violated, or the net count can never change. Second, C and CP symmetries must be violated, or matter and antimatter remain exact mirror outcomes. These conditions are not aesthetic preferences, they are logical gates, and without passing them the universe cannot produce a net excess. Sakharov proposed these conditions in 1967, at a time when the Standard Model was still being assembled. His insight was to translate a cosmic fact into dynamical requirements, turning a mystery into a research program. The checklist is still used because it is not tied to one model, but to logical necessity. It is one of those rare moments where a simple statement organizes decades of work. Third, the universe must be out of equilibrium, or forward and reverse reactions cancel perfectly. Expansion helps by cooling the plasma and diluting reaction rates. Phase transitions can help by creating bubble walls or changing rates abruptly, breaking the detailed balance that equilibrium enforces. In visual terms, equilibrium looks like a perfectly mixed fog, while out of equilibrium looks like fronts, gradients, and moving boundaries. Out of equilibrium is the hardest requirement to satisfy naturally, because equilibrium is what hot systems prefer. In equilibrium, CP-violating effects can exist, yet they often average to zero when every process is matched by its inverse. The universe needs a one-way street, even if it is only briefly one way. The question is almost unsettling. What event or what instability provided that brief arrow? The standard model contains CP violation, but it appears too small to explain the observed asymmetry. It also has baryon number violating processes through electroweak sphalerons at high temperature, but the overall effect depends on the nature of the electroweak transition. Many calculations suggest new physics is needed, which makes the asymmetry a clue pointing beyond known particles. The imbalance becomes a message written in the oldest light, asking for an extension of the rules. CP violation in the standard model arises primarily from the complex phase in the quark mixing matrix, and it has been measured in K and B meson systems. Those measurements are triumphs of precision, yet when inserted into baryogenesis calculations they fall short by orders of magnitude. The universe seems to be asking for an additional source of CP violation. That request is specific enough to guide experiments, yet broad enough to keep theorists uneasy. Sphalerons add another layer of intrigue. They are non-perturbative configurations in the electroweak theory that allow baryon and lepton number to change while conserving B-L. At high temperatures, these transitions can be rapid, and they can either help create baryons or erase them, depending on when the asymmetry is generated. In the narrative, sphalerons act like a cosmic accountant, capable of rewriting the ledger under the right conditions. One possibility is electroweak baryogenesis, where the electroweak transition is strongly first order. In that case, expanding bubbles of the broken symmetry phase sweep through the plasma. CP-violating interactions at the bubble walls can bias particle transport, creating an asymmetry that sphalerons partially convert into baryon number. The mechanism is delicate because it requires both the right kind of transition and the right kind of CP-violating physics. The bubble wall picture is visually rich, and it is also physically specific. Imagine a foggy plasma, and within it, expanding regions where the Higgs field has chosen its non-zero value. The walls are thin compared to cosmic scales, but they are thick enough to act like filters, reflecting and transmitting particles differently. The camera can track a wall as a moving horizon, one that changes what reactions can occur on either side. In these scenarios, particles hitting the wall can experience CP-violating phases that slightly favour matter over antimatter in how they scatter. That bias creates a chiral imbalance in front of the wall, and sphalerons in the symmetric phase can convert that imbalance into baryon number. When the wall passes, the broken phase can lock in the result by suppressing further sphaleron activity. The universe, for a moment, behaves like a chemical reactor with a moving boundary condition. Another possibility is leptogenesis, tied to neutrino physics and the mystery of neutrino mass. If heavy right-handed neutrinos existed early on, their decays could violate CP and occur out of equilibrium. The resulting lepton asymmetry can be reprocessed into baryons by sphalerons before electroweak symmetry breaking completes. This route is attractive because it uses ingredients that already feel plausible, given what we now know about neutrino mixing. Leptogenesis is compelling because it connects to the seesaw idea, where light neutrino masses emerge from mixing with very heavy states. The heavy neutrinos would be invisible in today's accelerators if their masses are enormous, yet their early universe decays could leave a permanent mark. The cosmos becomes the detector for particles we cannot otherwise reach. It is a reminder that the early universe explored energies far beyond our machines, even if only briefly. The decays must satisfy a delicate balance. They need to happen when the universe is hot enough to produce the heavy neutrinos, but not so hot that inverse reactions keep everything in equilibrium. They must also violate CP, so that decay products carry a slight preference for leptons over antileptons. Small asymmetries must be protected long enough to matter, which is a recurring theme in early universe physics. These mechanisms are not just add-ons to the narrative, because they connect cosmic survival to laboratory measurements. CP violation can be searched for in meson decays and electric dipole moments. Neutrino properties can be probed through oscillations, mass ordering, and the question of whether neutrinos are their own antiparticles. Every improved constraint tightens the plot, ruling out some stories while making others more urgent. Electric dipole moment experiments are especially telling, because they test new CP-violating physics with extraordinary sensitivity. A non-zero dipole moment in the neutron or electron would be a sign that the standard model is incomplete in exactly the direction baryogenesis seems to demand. In that sense, tabletop experiments and the early universe share the same plot. The smallest measured wobble in a lab could echo the oldest imbalance in the cosmos. The universe's matter content therefore becomes a forensic problem, not a philosophical one. We are not asking why matter exists in general, but why this specific imbalance exists. The central question about nothing is still present, but it now shares the stage with a measurable asymmetry. The mystery is sharpened by the fact that the asymmetry is tiny, because tiny effects are often the hardest to explain cleanly. There is also a sobering implication hidden in the numbers. If the asymmetry were even slightly smaller, the universe would be mostly radiation with trace baryons, and structure would struggle to form. If it were much larger, the thermal history and light element abundances would look different, and the sky would not match what we see. The cosmos seems balanced on an edge, and the edge is defined by a part per billion preference. Neutrinos are central characters in this era, because they are abundant and elusive. They decouple early, when weak interactions can no longer keep up with expansion. After decoupling, they stream freely, carrying energy and affecting the expansion rate during nucleosynthesis and later epochs. Visually, they are like a silent wind passing through everything, present everywhere yet leaving only gravitational fingerprints. Decoupling is a competition between interaction rates and the Hubble expansion rate. When the universe expands faster than neutrinos can scatter, they effectively stop exchanging energy with the plasma. From then on, their momentum distribution simply redshifts, a fossil of the temperature at which they last interacted. The concept is simple, but the consequence is profound. A relic background of neutrinos should still fill space today. Although neutrinos barely interact, their sheer number makes them cosmologically important. They contribute to the radiation density, altering how quickly the universe expands at early times. That expansion rate influences when neutrons and protons fall out of equilibrium, which in turn affects helium production during nucleosynthesis. The early universe is a network of coupled effects, where even nearly invisible particles can steer outcomes. Their tiny masses matter because they behave as hot dark matter, smoothing structure on small scales. Precision cosmology constrains the sum of neutrino masses through the CMB and large-scale structure. The constraints are not just numbers because they limit which particle physics models can fit both the sky and the lab. Each improved measurement narrows the range of possible neutrino stories, and with it the range of possible early universe histories. Hot dark matter free streams, which means it moves fast enough to wash out small density perturbations. This effect is subtle but measurable, because it changes the clustering pattern of galaxies and the lensing of the CMB. The sky therefore contains a neutrino signature, even if no neutrino is directly seen. The universe becomes a detector not by catching particles, but by recording what their motion prevents. Dark matter enters here as another survival problem, but on a different axis. The universe's visible matter is only a small fraction of the total gravitating matter. Something unseen shapes the growth of structure, deepening potential wells that baryons later fall into. The question is not only what dark matter is, but why it behaves with such restraint. Massive enough to sculpt the cosmos, quiet enough to remain hidden. The evidence for dark matter is layered and historical. Galaxy rotation curves, gravitational lensing, and the dynamics of clusters all point to missing mass. Cosmology adds a global accounting showing that baryons alone cannot explain the observed pattern of anisotropies in the CMB. The story has the feel of a long investigation, where each decade added a new line of evidence pointing to the same invisible culprit. Reheating and subsequent cooling can produce dark matter candidates in several ways. A thermal relic freezes out when annihilations become too rare, leaving a stable abundance set by interaction strength. A non-thermal relic can be produced by decays, misalignment, or gravitational production, depending on the candidate. The common thread is timing. When reactions stop, the universe keeps whatever is left. Freeze out is another timing story, and it uses the same logic as neutrino decoupling. While annihilations are frequent, dark matter stays in equilibrium with the plasma, and its abundance tracks a thermal distribution. As the universe expands and cools, the annihilation rate drops, and a relic population remains. The camera can show a thinning storm of collisions until the remaining particles simply drift, no longer finding partners to annihilate with. In the simplest thermal picture, the final abundance is inversely related to the annihilation cross-section. A larger cross-section keeps dark matter annihilating longer, leaving less behind, while a smaller cross-section leaves more. This is why the WIMP miracle once seemed so attractive, because weak-scale interactions give a relic density near what is observed. Even if the miracle is not the answer, it taught cosmologists how deeply relic abundances encode microphysics. WIMPs are the classic thermal relic idea, motivated by weak-scale interactions and a natural relic density. Axions arise from a different problem in particle physics and can be produced through field dynamics rather than particle collisions. Sterile neutrinos, hidden sector particles, and other candidates widen the menu because the standard model does not supply a stable, cold component with the required abundance. The list is long because the evidence is gravitational, and gravity does not reveal the particle's identity. Axions, in particular, are born from a field story rather than a collision story. Their abundance can come from misalignment, where a field starts displaced from its minimum and later oscillates as the universe cools. Those oscillations behave like cold matter, even though the underlying physics is wave-like. Visually, you might show a smooth field beginning to slosh, then settling into a persistent invisible rhythm that carries energy like mass. Sterile neutrinos, if they exist, would mix slightly with ordinary neutrinos, and they could be produced in the early plasma through that mixing. Depending on their mass and production history, they could be warm rather than cold, which would leave a different imprint on small-scale structure. The sky is again a laboratory, distinguishing possibilities by their gravitational fingerprints. In a warm scenario, the smallest filaments blur, as if the cosmic web were drawn with a softer brush. Even without identifying the particle, cosmology tells us what dark matter must do. It must be long-lived, mostly non-relativistic by the time structure grows, and weakly interacting with light. Those properties allow it to form the gravitational scaffolding that later becomes the cosmic web. The remarkable point is that we can describe its job with confidence, even while its name remains unknown. The phrase, weakly interacting with light, is not just about invisibility. If dark matter scattered strongly with photons or baryons, it would participate in acoustic oscillations and smear out structures, contradicting observations. Its silence is part of its job description because it must clump without being pushed around by radiation. In the narrative, dark matter is the unseen architect, shaping the blueprint while leaving no direct signature in the glow. This scaffolding links back to inflation's tiny perturbations. Inflation provides the initial pattern of small curvature variations. Dark matter amplifies that pattern efficiently after it decouples from radiation because it does not feel photon pressure and can begin clumping earlier. The universe is consistent in its logic. Tiny seeds become large structures because gravity has time and the right kind of matter to work with. Here the visuals can zoom out to a ghostly web forming in slow motion. Density peaks deepen, and valleys evacuate, creating a filamentary network. The pattern begins as a faint statistical texture in the CMB, but gravity turns it into architecture. The camera can drift along filaments like highways of mass, with nodes brightening where galaxies will one day ignite. Baryons cannot clump freely at first because they are coupled to photons in the hot plasma. Radiation pressure resists compression, creating acoustic oscillations that later appear as peaks in the CMB power spectrum. Dark matter does not participate in those oscillations, but its gravity still drives the overall growth. This division is crucial because it explains why the CMB is both a snapshot of plasma physics and a map of future structure. In the plasma, electrons scatter photons efficiently through Thomson scattering, and protons are tied to electrons by electric forces. That coupling makes baryons feel the photon bath like a stiff spring, so compressions rebound and rarefactions follow. The resulting oscillations are frozen into the CMB as a harmonic series of peaks. In visuals, pressure waves can ripple outward like sound in a glowing fog, then freeze into a pattern as the universe becomes transparent. Dark matter, by contrast, is not dragged by photons, so it can start forming potential wells earlier. Baryons later fall into those wells once they are released from photon pressure. This division of labour, dark matter building the scaffolding, baryons painting it with luminous matter, shapes the later universe. It also means the first structures are, in a sense, built in darkness, long before starlight appears. As the universe expands, it cools through the era of nucleosynthesis and beyond. Light nuclei form in the first minutes, setting the primordial abundances that later chapters anchored as evidence. After that, the universe remains a plasma for hundreds of thousands of years, because photons keep electrons from settling into atoms. The timescales widen dramatically here, and the story shifts from explosive change to patient cooling. The persistence of the plasma is a consequence of the enormous photon-to-baryon ratio. Even when the average photon energy drops below the hydrogen binding energy, the high-energy tail of the blackbody distribution still contains enough photons to ionize atoms. The universe must cool further before neutral atoms can survive in bulk. It is a reminder that averages can mislead, because the rare energetic photons can control the chemistry of the whole cosmos. Recombination is the turning point when electrons bind to nuclei to form neutral atoms. The name is misleading, because it is the first combination of electrons with protons in a stable way. Once atoms form, photons scatter far less often, and the universe becomes transparent. The visuals can show charged particles gradually pairing off, as if the plasma is finally allowed to settle into calmer neutral configurations. Recombination is not instantaneous, and it is not a single temperature threshold. It is a kinetic process governed by atomic transition rates, the expansion rate, and the escape of photons from resonant lines. In practice, the ionization fraction drops over a range of redshifts, creating a finite thickness to the last scattering surface. That thickness matters, because it slightly blurs the CMB image, like a photograph taken through a thinning mist. A vivid way to picture it is as a fog lifting at dawn. Before recombination, the universe is like a dense cloud bank where light travels only a short distance before scattering. As neutral atoms form, the fog thins, and suddenly the horizon opens. The camera can pull back and reveal depth for the first time. Distance becomes visible, and the universe gains a new kind of scale. Photon decoupling is the release of the cosmic microwave background. The CMB is not light from the Big Bang's first instant, but from the last scattering surface when the plasma cleared. Its near-perfect blackbody spectrum preserves the thermal history, and its anisotropies preserve the primordial perturbations. The CMB is therefore both an ending and a beginning of opacity and a beginning of cosmic visibility. The blackbody spectrum is one of the cleanest measurements in all of science, and it is hard to fake. It tells us the early universe was once in excellent thermal equilibrium, because only repeated interactions can produce such a precise Planck distribution. The CMB is therefore a photograph of a thermal state, not merely a glow. In the documentary, the spectrum can appear as a smooth curve, almost too perfect, hinting at the disciplined physics behind the chaos. The anisotropies are tiny, at the level of tens of microkelvin, yet they carry enormous information. They encode density variations, gravitational redshifts, and Doppler shifts from moving plasma. They also preserve the phase coherence expected from inflation, where perturbations begin as correlated quantum fluctuations. That coherence is a subtle clue, because it suggests the seeds were laid down with a common origin, rather than random, uncorrelated noise. The CMB also carries polarization patterns that encode the velocity field and density gradients at last scattering. These patterns cross-check the inflationary story of coherent initial conditions. They also constrain the number of relativistic species and the expansion rate, tying back to neutrinos and any hidden radiation. The polarization is like a second layer of the photograph, faint but structured, revealing motion and geometry that temperature alone cannot show. Polarization arises because Thomson scattering prefers certain directions when the incoming radiation has a quadrupole anisotropy. The resulting E-mode pattern has been measured with high precision, and it matches the acoustic picture. The search for primordial B-modes continues because they would be a signature of gravitational waves from inflation. If found, they would connect the quiet polarization of the CMB to the most violent expansion the universe ever experienced. Constraints on relativistic species are often phrased as an effective number of neutrino-like degrees of freedom. If a hidden light particle existed and contributed to radiation density, it would shift the damping tail and peak structure of the CMB. The absence of large deviations is a quiet but powerful statement about what the early universe contained. Even silence is evidence here, because the CMB is sensitive to any extra radiation that would change the expansion rate. The universe after recombination is suddenly larger in one crucial sense. Light can travel long distances without constant interruption, allowing information to propagate and structures to be seen. The cosmos becomes a place where photons can carry a record and where gravity can work in relative darkness. The stage is set for a long era in which matter slowly gathers, while radiation becomes a background whisper. In visual terms, the camera can finally pull back and see. Before, every scene is close-up, crowded and opaque, with collisions everywhere. After decoupling, space becomes clear, and the first long lines of sight open across expanding darkness. The glow of the CMB recedes into the background, like the last light of an earlier age fading behind the foreground of structure. But the chapter's climax is not transparency, it is survival. Matter wins by a margin so small it seems almost absurd, yet it is enough. After most matter and antimatter annihilate, the leftover baryons become the atoms that later form stars and planets. The universe is not built from a grand surplus, but from a narrow escape written into the laws. It is worth lingering on the annihilation itself, because it is both violent and efficient. When baryons and antibaryons meet, they convert their mass into photons, flooding the universe with radiation. What remains is not a balanced mixture, but a thin residue that escaped simply because there was nothing left to annihilate with. The visuals can show pairs flashing into light, over and over, until the flashes become rare and the survivors drift apart. That leftover is not a miracle in the narrative sense, because physics can outline the required conditions. It is a mystery in the scientific sense because we do not yet know which mechanism supplied the needed CP violation and out-of-equilibrium dynamics. The imbalance is both a fact and a signpost pointing beyond the standard model. The question hangs in the air: which hidden ingredient tipped the scales, and why was it so precisely small? The mystery is sharpened by how well we understand the rest of the thermal history. We can compute nucleosynthesis, recombination, and CMB anisotropies with impressive accuracy. Against that backdrop, baryogenesis stands out as an unfinished paragraph in an otherwise coherent story. It is the place where our equations still gesture, rather than conclude. This is where we connect back to the documentary's opening hook about nothing and time. Even if the universe can begin without a classical before, it still must navigate a gauntlet of symmetry and annihilation. Existence depends not only on a beginning, but on a tiny broken symmetry that prevents everything from cancelling. The vacuum can inflate, fields can reheat, particles can appear, yet without that bias, the universe would still erase itself. And that raises a thought that is difficult to avoid. If the laws of physics had been perfectly symmetric in their outcomes, the universe would be bright, expanding and empty of structure. The fact that we are here implies that somewhere, in the early heat, nature chose a slight preference. Was that preference inevitable, or was it contingent on details we have not yet uncovered? Now the story changes pace, because the violent early transformations give way to slow accumulation. Once matter exists and light can travel freely, gravity begins its long, patient work. Tiny fluctuations become halos, halos become galaxies, and galaxies become the environments where chemistry can persist. The documentary can slow its rhythm here, letting the viewer feel the shift from microphysical drama to cosmic construction. In the new, transparent universe, gravity is no longer competing with photon pressure in the same way. Baryons can finally fall into dark matter potential wells, heating through shocks and cooling through radiation. The first halos are small, but they are the seeds of everything that follows. In visuals, faint knots in the dark matter web begin to brighten as gas collects, compresses, and prepares for the first ignition. We end with a transition that points forward to structure and complexity. The early universe was a particle accelerator and a phase transition laboratory. The next chapter follows the cooled remnants as they assemble into the first stars, the first heavy elements, and the first durable sources of light. Transition: once matter survives and the universe turns transparent, gravity starts its slow masterpiece, shaping fluctuations into the cosmic web. After recombination, the universe turns transparent, but it remains almost entirely dark to human eyes. The cosmic microwave background streams freely through space, its photons no longer trapped by charged plasma. Yet those photons are already cooling, stretched to longer wavelengths by expansion. Visually, the scene is quiet and immense, an afterglow filling everything, uniform to 1 part in 100,000. That faint mottling matters, because it is the fossil imprint of earlier sound waves in the primordial plasma. Tiny density differences seeded earlier now become the only instructions gravity needs. Structure formation starts with what we cannot see, and that invisibility is not poetic license. Cold dark matter decouples from radiation early, so it can begin clumping while baryons remain pressured by photons. In the simplest picture, dark matter feels gravity and little else, so it starts to fall into its own slight overdensities. Baryons, by contrast, are still coupled to light before recombination, and that coupling acts like a spring. Photon pressure resists compression, and the baryon fluid oscillates, leaving the baryon acoustic oscillation scale as a standard ruler. When recombination ends, that pressure support collapses, and ordinary matter can finally respond to existing gravitational wells. In simulations and surveys, the invisible component collapses first, building gravitational wells that guide everything luminous. We infer those wells through rotation curves, gravitational lensing, and the way galaxies cluster on large scales. The evidence is indirect but convergent. Different methods point to the same missing mass. Gravity works inside an expanding space-time, and that tension shapes the cosmic web in a very specific way. Expansion stretches distances on average, but overdense regions resist, slowing locally and pulling in more mass. The competition is encoded in the growth factor of perturbations, which changes as the universe's contents change. If you could watch the early universe in fast motion, you would see a subtle pattern sharpen into structure. Threads condense, junctions thicken, and broad regions evacuate into emptiness. The result is a network of filaments and nodes, with voids growing emptier as matter drains away. This web is not a metaphor because it is measured. Galaxy redshift surveys draw it in 3 dimensions, and weak lensing maps reveal it in projected mass. Even the intergalactic medium traces it, because hydrogen gas collects along the same filaments that dark matter defines. Dark matter halos form hierarchically, and the hierarchy is a consequence of the primordial power spectrum. Small halos collapse first, then merge into larger halos, assembling structure like a branching genealogy. This bottom-up growth is not a guess, because it matches clustering statistics and the lensing maps of mass. The earliest halos are small, and their gravity is shallow, so they are easily disturbed. As they merge, they undergo violent relaxation, redistributing particle energies until a stable halo profile emerges. In that process, subalos survive as orbiting clumps, and those clumps later host satellite galaxies. Baryons fall into halos once photon pressure releases them, but the fall is not gentle. Gas shocks and heats as it accretes, converting gravitational potential energy into thermal energy. For massive halos, the gas can reach millions of degrees, becoming a hot, ionized atmosphere. Cooling is the gatekeeper, because without it, gas cannot compress enough to form stars. At temperatures around 10,000 Kelvin, hydrogen line emission becomes efficient, and at higher temperatures, metal lines dominate if metals exist. In a metal-poor universe, cooling pathways are limited, and that limitation shapes the first luminous objects. The first stars ignite in a universe with almost no heavy elements, and that is a profound constraint. With only hydrogen and helium available, cooling is inefficient, so the earliest stars are likely massive and short-lived. Their formation may rely on molecular hydrogen, H2, which can radiate away heat even without metals. Visually, the first star-forming clouds are lonely islands inside a vast dark sea. A collapsing pocket of gas spins up, fragments imperfectly, and then produces a few brilliant blue-white beacons. Their light ends the cosmic dark ages, and their deaths begin chemical history. These population 3 stars are still partly hypothetical, but their consequences are not. Massive stars emit intense ultraviolet radiation, and they explode quickly, injecting energy and newly forged elements into their surroundings. The first supernovae may even be pair instability explosions, leaving no remnant and dispersing heavy elements widely. Reionization follows as ultraviolet photons from early stars and galaxies strip electrons from hydrogen again. The intergalactic medium becomes ionized, changing how light travels and leaving a measurable imprint in CMB polarization. This is a second transparency story, but driven by starlight rather than cooling. Reionization is also patchy, like dawn breaking unevenly across a landscape. Ionized bubbles grow around early galaxies, then overlap, and eventually fill most of intergalactic space. Quasar spectra reveal this transition through the GUN, Peterson Trough, a telltale absorption signature of neutral hydrogen. Galaxies form where gas can settle inside halos, but the process is violent and self-regulating. Gas inflow fuels star formation, and star formation triggers feedback that can halt it. Galaxies are not simple containers of stars, because they are ecosystems of inflow, outflow, and recycling. Inflow arrives along filaments, sometimes as cold streams that penetrate hot halos. Outflow leaves as winds, carrying metals and energy into the circumgalactic medium. Recycling returns gas later, because expelled material can cool, slow, and fall back, an extended breathing cycle across billions of years. The earliest galaxies look nothing like the Milky Way's calm disk. They are compact, irregular, and clumpy, with giant star-forming regions dominating their light. High redshift observations show these systems as small smudges, but behind the smudges is a turbulent, gas-rich reality. Mergers are a primary engine of galaxy evolution, and they are a natural outcome of hierarchical growth. When halos merge, their galaxies interact, stirring gas, triggering starbursts, and reshaping stellar orbits. Over cosmic time, repeated mergers help explain why some galaxies become ellipticals while others preserve disks. A major merger can scramble a disk into a spheroid because stellar orbits become randomized. Gas can lose angular momentum through tidal torques, funneling inward and feeding central starbursts. In the visual language of the sky, tidal tails arc outward like luminous scars marking the encounter. Minor mergers matter too because they are frequent. A small satellite can thicken a disk, seed a stellar halo, and deliver fresh gas. Streams of disrupted stars wrap around galaxies, and in the Milky Way we still see those streams as evidence of ongoing assembly. Disks form when gas retains angular momentum while cooling, and angular momentum is the memory of earlier cosmic torques. Rotation supports the disk against collapse, while spiral density, waves, and turbulence redistribute gas. The disk becomes a long-lived star factory, but only if feedback does not blow the gas away. Spiral arms are not rigid structures, but patterns, regions where gas compresses and forms stars. As gas enters an arm, it shocks, cools, and collapses into molecular clouds. The resulting star clusters light the arms in blue, while older stars drift onward, leaving a layered, rotating record. Feedback is the crucial break, because star formation would otherwise run away. Supernovae inject energy and momentum, driving winds that remove gas from small galaxies and enrich the surrounding medium. Without this regulation, models overproduce stars, creating galaxies that are too bright and too massive. Feedback is not only explosions, because massive stars also produce radiation pressure and stellar winds. Ultraviolet photons ionize nearby gas, heating it and raising the pressure that resists further collapse. In small halos, a few energetic events can unbind gas entirely, delaying star formation for long periods. Black holes add a second, deeper feedback channel, and their influence scales with their appetite. As supermassive black holes accrete, they can launch jets and heat surrounding gas, suppressing cooling in massive halos. This helps explain why the largest galaxies stop forming stars and become red and quiescent. The historical arc here is striking, because black holes were once treated as exotic curiosities. Quasars, discovered as bright radio sources, turned out to be distant galactic nuclei powered by accretion. Today, the tight correlation between black hole mass and galaxy bulge properties suggests coevolution rather than coincidence. Accretion disks convert gravitational energy into light with extreme efficiency. A small amount of infalling mass can outshine an entire galaxy of stars, and jets can pierce intergalactic space. In clusters, those jets inflate bubbles in hot gas, visible in X-rays as cavities, like fingerprints of invisible engines. The shapes of galaxies across cosmic time record this competition between inflow and feedback. Early galaxies are clumpy and gas-rich, because accretion rates are high and disks are unstable. Later galaxies are more orderly on average, because gas supply declines and mergers and feedback reshape what remains. This trend is also written in colour. Blue galaxies are actively forming stars, dominated by short-lived massive stars, while red galaxies are older and quieter. The shift from blue to red is not just aging, because it often requires quenching mechanisms that cut off the fuel. Clusters and groups become the largest bound structures, built from many merged halos over cosmic time. Their hot intracluster gas shines in X-rays and reveals deep gravitational potentials. Lensing shows that most of the mass is still dark, even where baryons glow. In a cluster, Galaxies move at thousands of kilometers per second, and the environment is harsh. Ram pressure can strip gas from spirals, shutting down star formation and transforming them into gas-poor systems. The cluster is a laboratory where gravity, plasma physics, and galaxy evolution intersect. This is the first major climax of cosmic evolution because it turns initial randomness into architecture. Quantum fluctuations become a cosmic web, and the web becomes galaxies filled with long-lived energy sources. The universe begins to look less like an initial condition and more like a machine that builds complexity. Transition. The same gravity that assembles galaxies also forges the engines that change chemistry. Stars are those engines, and their physics is both simple and decisive once the threshold is crossed. Gravity compresses gas until the core is hot enough for nuclear fusion, typically millions of Kelvin. Fusion converts mass into energy, and that energy pushes outward, balancing collapse for millions to billions of years. This balance is hydrostatic equilibrium, and it is a dynamic truce rather than a permanent peace. If the core cools or the fuel changes, gravity gains the advantage and contraction resumes. That contraction raises temperature again, unlocking new fusion stages, and the star evolves through a sequence of thermonuclear regimes. The first fusion step is hydrogen to helium, which powers main sequence stars and stabilizes them for long durations. In stellar cores, quantum tunneling allows protons to fuse despite electric repulsion. The rate is slow enough to make stars stable, and stability is what gives time for complexity. In the Sun, hydrogen fusion proceeds mainly through the proton chain, producing neutrinos as a byproduct. Those neutrinos escape almost immediately, carrying direct information from the core. Detecting them was once a puzzle, and resolving the solar neutrino problem helped confirm neutrino oscillations, new physics revealed by starlight. In more massive stars, hydrogen burning often proceeds through the CNO cycle, which uses carbon, nitrogen, and oxygen as catalysts. That dependence means metallicity affects stellar evolution, especially in the early universe. Even when the catalyst is scarce, the star's higher core temperature can compensate, changing lifetimes and luminosities. Helium burning comes next in more massive or evolved stars after the core contracts and heats further. 3 helium nuclei can combine through the triple alpha process to form carbon. Carbon is not an inevitable product of the Big Bang, because Big Bang nucleosynthesis stops at light elements. The triple alpha process depends sensitively on a resonant energy level in carbon-12, a fact predicted by Fred Hoyle. That prediction is a famous example of theory guided by cosmic necessity, because without it, carbon would be rare. The resonance is real, and it is one reason the universe can build complex chemistry at all. Oxygen forms when carbon captures helium, and heavier elements follow in massive stars through successive burning shells. Fusion builds nuclei up to iron, because iron is a binding energy endpoint for energy-producing fusion. Beyond iron, making heavier nuclei requires energy input, not energy release. In the late life of a massive star, the interior becomes layered like an onion. Hydrogen burns in an outer shell, helium burns deeper, and then carbon, neon, oxygen, and silicon burn in sequence. Each stage is shorter than the last because higher temperatures accelerate reactions and neutrino losses drain energy rapidly. Iron is the dead end for fusion-powered support, and that dead end triggers catastrophe. When an iron core grows too massive, electron degeneracy pressure can no longer hold it up. The core collapses in a fraction of a second, and densities rise to nuclear values. Supernovae provide the needed energy input and more, creating extreme conditions for nucleosynthesis. When massive stars collapse, shockwaves and neutrino-driven processes create environments rich in free neutrons. Elements heavier than iron can form through rapid neutron capture, and then disperse into space. The details are still being refined, because supernova physics is complex. Neutrinos carry away most of the gravitational energy, and a small fraction must couple to matter to revive the shock. Multidimensional simulations show convection and instabilities that help the explosion succeed. Turbulence becomes part of the mechanism. Neutron star mergers add another heavy element factory, and their discovery is recent in historical terms. Their colonovae can produce large amounts of R-process material, including gold and uranium. The relative contributions of supernovae and mergers remain an active question, but the conclusion is firm: heavy elements require stellar death. The gravitational wave event GW-08 and UNT7, linked neutron star mergers to kilonova light and heavy element production. In that moment, a new messenger joined astronomy, and it confirmed an old suspicion. The universe does not only shine, it also rings, and those vibrations reveal where matter is forged. Type E supernovae add a different enrichment pattern, and they are crucial for iron. White dwarfs in binaries can explode, producing iron peak elements efficiently. Over time, this changes the chemical fingerprints of galaxies, letting astronomers reconstruct star formation histories from stellar abundances. Type Ia events also became cosmological tools because their brightness can be standardized. Observations of distant Type Ia supernovae revealed accelerated expansion and helped establish dark energy. In a sense, the same explosions that enrich galaxies also measure the universe's fate. Every atom in a rocky planet is a record of multiple stellar generations, layered across time. Hydrogen and helium dominate the cosmos, but carbon, oxygen, silicon, and iron are manufactured later and locally. The universe becomes habitable only after it becomes chemically diverse. This chemical diversity spreads through winds, supernova remnants, and the mixing of galactic gas. Metals cool gas more efficiently, allowing smaller clouds to fragment and form lower mass stars. That shift changes the stellar population, increasing the number of long-lived stars that can host stable planetary systems. Metallicity becomes a clock for habitability, though it is not a simple one. Early galaxies have low heavy element content, limiting dust and cooling, and the formation of small rocky planets. As enrichment spreads, dust grains become common, and planet-building raw material accumulates in disks. Dust is more than debris, because it is a chemical surface and a thermal regulator. It helps molecules form, including H2, and it shields dense regions from destructive radiation. In images of star-forming regions, dust appears as dark lanes and glowing pillars, sculpted by nearby starlight. Transition. Once stars can make heavy elements, gravity can build worlds where chemistry persists. Planet formation begins in protoplanetary disks around young stars, and those disks are now directly observed. Disks form naturally from collapsing clouds with angular momentum, leaving a rotating plane of gas and dust. Within that disk, tiny grains collide and stick, starting a long climb toward planets. The visuals are striking: a young star surrounded by a thin, luminous ring with gaps and spirals etched into dust. ALMA images show these structures in nearby star-forming regions, implying that planet formation begins early. The disk is not smooth, because pressure bumps and turbulence create traps where solids concentrate. Dust growth is the first bottleneck because sticking is fragile at higher collision speeds. Micron grains become pebbles, and pebbles drift inward through gas drag, threatening to fall into the star. Models invoke streaming instabilities and pebble accretion to concentrate solids fast enough to survive. Streaming instability is a collective effect, where solids and gas interact to create clumps. As pebbles slow the gas locally, they reduce headwind drag, allowing more pebbles to pile up. Once the density is high enough, self-gravity takes over and the clump collapses into a planetesimal. Planetesimals form when dense clumps of pebbles collapse under their own gravity, crossing a critical threshold. Once kilometre-scale bodies exist, gravity takes over, accelerating growth through runaway and oligarchic accretion. Collisions become constructive at first, then increasingly violent. In runaway growth, the largest bodies grow fastest because their gravity enhances their collision cross-section. Later, oligarchs dominate local zones, stirring smaller bodies and limiting further runaway. The disk becomes a chaotic construction site, where impacts both build and erase, and where heat is generated by violence. Rocky planets form inside the snowline, where water ice cannot remain stable in the warm inner disk. With less solid material available, growth is slower, but the resulting planets are dense and metal-rich. Giant planets form beyond the snowline more easily, because ices add mass to cores. The snowline is not fixed, because it moves as the disk evolves and the star brightens. That movement can change where water-rich material forms and where it is delivered. In our own system, this shifting boundary likely influenced the distribution of dry inner planets and icy outer bodies. Gas giants require a timing coincidence, and the clock is set by disk dispersal. A solid core must grow massive enough to accrete gas before the disk disperses, typically within a few million years. If the gas disappears too soon, the system produces ice giants or super-Earths instead. Once runaway gas accretion begins, the planet's envelope can grow rapidly. The forming giant opens gaps in the disk, altering gas flow and dust distribution. Those gaps are now seen in young disks, hinting that Jupiter-like planets may be common, even if their final orbits vary widely. Planetary migration reshapes many systems, and it is a natural outcome of disk-planet interactions. Interactions with the disk and with other planets can move worlds inward or outward, mixing compositions and destabilizing orbits. Our solar system may be a relatively calm outcome, not a universal template. Hot Jupiters, discovered first among exoplanets, are evidence that migration can be dramatic. A giant planet close to its star likely formed farther out, then spiraled inward through disk torques or later gravitational scattering. That history can disrupt inner rocky planets, or it can leave them intact depending on timing. Differentiation follows when planets heat internally, and heat is an unavoidable byproduct of formation. Impacts, radioactive decay, and gravitational compression melt interiors, allowing dense iron to sink and silicates to rise. Cores generate magnetic fields in some cases, and mantles drive volcanism and long-term cycling. A magnetic field can shield an atmosphere from stellar wind stripping, though it is not the only factor. Atmospheres also depend on gravity, composition, and the star's activity history. In the early stages, young stars flare more often, bathing planets in high-energy radiation that can erode or transform atmospheres. Volatiles are the next requirement for life as we know it, and their delivery is a complex story. Water, carbon dioxide, nitrogen, and organics can be delivered by hydrated minerals, comets, and icy planetesimals. The balance depends on formation location, migration history, and the violence of late impacts. In the inner solar system, Earth's water may come largely from carbonaceous asteroids rather than comets. Isotopic ratios, such as deuterium to hydrogen, serve as chemical fingerprints. These measurements turn meteorites into time capsules, preserving evidence of where material formed and how it moved. Oceans become possible when temperature and pressure allow liquid water to persist, but persistence requires stability. A stable climate requires feedbacks that buffer extremes, and plate tectonics may help by cycling carbon. These are not guaranteed outcomes, because many planets lose atmospheres or freeze or overheat. The carbonate, silicate cycle is one proposed stabilizer, slowly adjusting atmospheric CO2 through weathering and volcanism. Over geological time, it can counteract changes in stellar brightness, keeping temperatures within a habitable range. Yet it depends on active geology, which itself depends on internal heat and composition. Habitability is therefore a chain of contingencies, but it is also a chain of physics that can be studied. Gravity builds a planet, chemistry builds an atmosphere, and energy flows drive disequilibrium. Life, if it appears, must exploit that disequilibrium to persist. Transition. When worlds stabilize, the mystery shifts from structure to emergence. The origin of life is not a single accepted story, but there are plausible pathways grounded in chemistry and thermodynamics. The core requirement is a system that can store information, replicate with variation, and harness energy to maintain order. Chemistry must cross a threshold where selection can begin. That threshold is subtle, because it is not just complexity, but functional complexity. Many molecules can form spontaneously, yet few participate in networks that sustain themselves. The question becomes, what environments repeatedly produce networks that are both robust and evolvable? Energy gradients are the universal fuel, and they appear wherever a planet is out of equilibrium. Sunlight drives photochemistry at surfaces, while geothermal heat drives reactions in crust and ocean. Life does not require a specific energy source, but it does require a persistent gradient that can be tapped. In plain terms, life needs a free energy budget, like a city needs a power grid. Without a gradient, chemistry relaxes toward equilibrium, and reactions stall. With a gradient, reactions can be coupled, and improbable structures can be maintained long enough to replicate. Hydrothermal vents offer one compelling setting, especially alkaline vents on the ocean floor. They provide chemical disequilibria, mineral catalysts, and compartment-like pores that can concentrate molecules. In alkaline vent models, proton gradients across thin barriers resemble the energy architecture used by modern cells. The vent environment is visually dramatic: dark water, shimmering heat, and mineral chimneys growing like underwater towers. Fluids rich in hydrogen meet carbon dioxide-rich seawater, and the resulting gradients can drive organic synthesis. Iron-sulfur minerals can act as catalysts, bridging inorganic chemistry and metabolic-like pathways. Another pathway emphasizes surface environments, where cycles can do chemical work. Wet-dry cycles can concentrate monomers and promote polymerization, and UV light can drive synthesis of key precursors. The challenge is integration, because building blocks, compartments, and metabolism must converge in one environment. UV light is both a hazard and a tool, because it can destroy molecules while also powering reactions. Early Earth lacked an ozone layer, so ultraviolet flux at the surface was intense. That intensity could have driven prebiotic chemistry, while also selecting for protective niches or rapid repair mechanisms. RNA World Ideas propose that early life used RNA for both information and catalysis, reducing the number of required innovations. Ribozymes show that RNA can perform chemical work, though prebiotic synthesis routes remain uncertain. Alternatives include peptide first, metabolism first, or mixed networks that later recruited genetic polymers. The deeper point is that modern biology may not preserve the earlier steps, because evolution overwrites its own scaffolding. Early replicators could have been simpler, messier, and more chemically diverse than anything alive today. If so, the origin of a life may be less like a single invention and more like a phase transition. Compartmentalization is a major step because it creates individuality. Fatty acids can form vesicles spontaneously, creating protocells that separate internal chemistry from the environment. Once compartments exist, selection can act on whole systems, not just on free-floating molecules. Vesicles can grow, divide, and encapsulate catalysts, at least in simplified laboratory settings. They can also maintain concentration differences, which is essential for metabolism-like cycles. The emergence of membranes turns chemistry into a set of competing lineages, each with its own internal conditions. The transition from chemistry to biology likely involved many intermediate stages, and patience is required. Autocatalytic networks could amplify certain molecules, while error-prone replication could explore variations. The key is that once heredity and selection begin, complexity can accumulate without foresight. This is where the narrative becomes both scientific and philosophical, because selection is a blind algorithm. It does not aim for intelligence, multicellularity, or consciousness, yet it can generate them given enough time and stable environments. The mystery is not that complexity can grow, but that the conditions for sustained growth can persist. Planetary context matters as much as chemistry, because environments set the boundary conditions. A stable liquid water window, availability of key elements, and protection from sterilizing radiation influence probabilities. Impacts can both deliver organics and reset environments, making early history a mix of construction and erasure. Early Earth likely faced intense UV, frequent impacts, and changing oceans and atmospheres, and the geological record is incomplete. Yet life appeared relatively early in Earth's history, perhaps within a few 100 million years after oceans stabilized. That fact raises a difficult interpretive question, because it can be read in more than one way. Is life an accident, or a tendency of complex matter in space-time, given energy flow and chemistry? One reading is selection bias, because observers only arise where life succeeded. Another reading is that chemistry plus energy gradients often yield self-organization, making life a common outcome. We cannot answer that with one planet, and we should be cautious about extrapolating from a single data point. Exoplanet surveys now show that planets are common, and many are Earth-sized. The next step is atmospheric characterization, searching for disequilibrium signatures that could indicate biology. The tools are improving rapidly, from transit spectroscopy to direct imaging concepts. A planet crossing its star imprints a tiny spectral signature, and that signature can reveal molecules like water vapor or carbon dioxide. In the future, separating a planet's faint light from its star's glare could reveal surface and atmospheric clues. Biosignatures are not simple stamps, because nature can mimic life's chemistry under some conditions. Oxygen can be produced abiotically in some scenarios, and methane can come from geology as well as life. The strongest cases will require multiple lines of evidence and context, not a single molecule. Context means understanding the star's spectrum, the planet's temperature, and the likely geochemical cycles. It also means searching for combinations that are hard to maintain without biology, such as oxygen with methane in the same atmosphere. Even then, interpretation will be probabilistic, because planets are complex systems. Technosignatures widen the search, extending it beyond biology to technology and industry. Artificial radio signals, industrial pollutants, or waste heat could reveal technology, though absence of evidence is not evidence of absence. The silence so far is a constraint on some possibilities, not a conclusion. It is also a reminder of scale, because the galaxy is vast and time is deep. Civilizations could be rare, short-lived, or simply quiet in ways we do not anticipate. The search forces a humbling question. Are we early, late, or alone within our observational horizon? Transition. While life struggles upward, the universe itself changes its long-term rules. Dark energy dominates the late-time expansion, and its discovery reshaped cosmology in the late 20th century. Like inflation, it behaves as a component with negative pressure, but its energy scale is vastly smaller, and its onset is billions of years later. The similarity is structural, and the difference is everything we do not understand. In the Friedmann equations, negative pressure contributes to accelerated expansion, and that is the key dynamical point. Ordinary matter and radiation dilute as space expands, while a cosmological constant remains constant per unit volume. As the universe grows, that constant-like component eventually wins, and acceleration begins. Accelerated expansion changes the future of structure, not by tearing things apart immediately, but by starving growth. Gravity can still bind galaxies and clusters locally, but the growth of new large-scale structure slows and effectively freezes. Over time, distant galaxies cross a cosmic horizon and become unobservable. This horizon is not a wall in space, but a limit in time, defined by light's ability to reach us. Light emitted beyond a certain distance will never reach us, because space expands too quickly in between. The observable universe becomes a shrinking island of information within a larger reality. Visually, imagine galaxies fading not because they dim, but because their light is stretched away. Their spectra slide toward the infrared, then toward radio wavelengths, and eventually beyond detectability. The sky becomes lonelier, and future astronomers, if any exist, would infer a smaller cosmos from local evidence. If dark energy is a true cosmological constant, the future tends toward a cold, dilute de Sitter-like state. Stars burn out, gas is locked in remnants, and entropy increases. Life, if it persists, must adapt to dwindling free energy sources. In that far future, the main sequence ends as star formation slows and then stops. White dwarfs cool, neutron stars drift, and black holes dominate the mass budget in compact form. The universe's remaining energy gradients become rarer, and the thermodynamic arrow continues forward. If dark energy evolves, the future could be stranger, and cosmologists keep multiple possibilities on the table. Some models allow a big rip, where expansion eventually tears apart bound structures. Others allow decay, which could slow acceleration and reopen structure growth, though evidence currently favours a constant-like behaviour. Observations constrain the equation of state parameter, often written as W, and so far it is close to -1. That closeness is itself mysterious, because it suggests vacuum-like behaviour without explaining its origin. Precision measurements of supernova, baryon acoustic oscillations, and lensing attempt to tighten the bounds. The cosmological constant problem returns with force, because it is a mismatch of staggering magnitude. Quantum field theory predicts vacuum energy contributions that are wildly larger than observed dark energy. The mismatch suggests missing physics, or a misunderstanding of how vacuum energy gravitates, or both. This is not a small discrepancy, but a crisis of scales. If naive estimates were correct, the universe would have accelerated violently from the start, preventing galaxies from forming. The fact that galaxies exist implies either cancellations, new symmetries, or a deeper framework that we have not yet grasped. This late-time mystery mirrors the early-time one, and the symmetry is hard to ignore. Inflation invoked vacuum-like energy to shape the beginning, and dark energy now shapes the end. The universe seems bracketed by 2 episodes of acceleration, each pointing to gaps in our understanding of nothing and vacuum, transition. After following the chain from quantum fluctuations to living cells, we return to the starting riddle. Cosmic evolution is a long causal ladder, and each rung is both constrained and contingent. Inflation seeds, perturbations, dark matter amplifies them, galaxies assemble, stars forge elements, planets condense, and chemistry explores pathways toward life. Each step is constrained by evidence, yet each step also depends on conditions we still debate. The ladder changes the meaning of the central question, because it reframes what needs explaining. If nothing existed before the Big Bang, then the existence of structure and life might seem like an added miracle. Yet the story we traced shows that complexity can emerge from simple rules, given time, gradients, and gravity. But the word nothing remains unstable, and physics itself forces that instability. A quantum vacuum is not emptiness, because it has fields, fluctuations, and energy that can drive expansion. Absolute nothing would have no space-time, no fields, and no time in which a trigger could occur. So we must separate two mysteries, even if they feel emotionally entangled. One is how the universe evolves from early conditions into galaxies, planets, and life, which physics can model and test. The other is why there is a universe with laws at all, which may demand a deeper theory of spacetime's origin. Chapter 6 ends at the edge where explanation becomes definition, and where language begins to strain. We can map the road from the first measurable moments to the emergence of observers. We still cannot say, with scientific clarity, what it means for reality to begin from nothing. Next chapter. We take the accumulated evidence and confront the boundary questions directly, asking which answers are meaningful, testable, and honest about what remains unknown. We return to the opening hook and tighten the language around it, because the hook is also the trap. Imagine no space to stand in, no clock to tick, no energy to measure, and no grid on which distance even makes sense. If time itself begins, before, may be undefined, and ordinary cause talk may misfire, like asking what lies north of the North Pole. First, we define what nothing can mean in this story, because the word carries hidden assumptions. Philosophical nothingness means no objects, no properties, no laws, and no space-time, no arena and no script. A quantum vacuum is not that, because it assumes fields, rules, and a background geometry, even if no particles are present. In quantum field theory, the vacuum still seethes with zero-point fluctuations and virtual excitations, which are real in their measurable effects. A deeper nothing in quantum gravity could mean no classical spacetime at all, yet still a mathematical structure that yields spacetime when conditions allow. This distinction matters because many, from nothing, claims quietly import a stage, then rename it. They start with a vacuum state, a path integral, or a boundary condition, then call it nothing, although each ingredient is already a kind of something. Physics can model those states with precision, but it cannot simply equate them with absolute non-being. Even the choice of a Hilbert space, or a set of allowed histories, is a commitment to structure. We also clarify what the Big Bang is, based on the evidence trail rather than the metaphor. The Big Bang is the start of the hot, dense expansion we can reconstruct from data, not a photographed flash of creation. It is anchored by expansion, nucleosynthesis, and the CMB's blackbody spectrum and anisotropies, which together form a tight, cross-checked narrative. When we say hot, we mean a thermal bath where particles constantly scatter, and when we say dense, we mean energy packed into a tiny volume by today's standards. It is not automatically a claim about an absolute beginning of reality, only the earliest chapter we can read with confidence. General relativity rewound points toward a singularity, but that is a warning label, not a destination. The singularity signals geodesic incompleteness and breakdown of classical spacetime description, where curvature invariants blow up and the equations lose predictive control. Historically, this is why singularities were treated with suspicion, even after Hawking and Penrose proved conditions under which they appear. The math is telling us the model has left its domain of validity. Like fluid equations at the scale of atoms, it motivates quantum gravity, not a confident statement that infinity happened. So we compare the leading proposals that try to replace the singular boundary without pretending the problem is solved. Quantum cosmology proposals treat the universe as a quantum system with a wave function, which means initial conditions become part of the quantum description. Hartley, Hawking no boundary, replaces a sharp beginning with a smooth Euclidean cap, where time behaves like a spatial direction and the geometry closes off gently. Visually, it is less like a cliff edge and more like the rounded pole of a sphere. No boundary to fall from. Vilenkin-style tunneling treats the universe as a quantum transition into an expanding space-time, with probabilities defined by boundary conditions that select which histories are allowed. These models aim to answer why there is a classical expanding universe at all, rather than a frozen quantum superposition. They try to avoid a singular start and reduce the need for a prior time parameter, which would smuggle in the very before we are questioning. Their weakness is interpretive because tunneling usually presumes time, and the measure problem shadows probability statements. When you ask what is more likely, you must define what counts as a comparable possibility, and that definition can quietly steer the conclusion. Next are bounce and cyclic scenarios, which keep time but change the earliest chapter, turning a beginning into a transition. In loop quantum cosmology, quantum geometry effects can produce a bounce when density approaches the Planck scale, because discreteness in area and volume alters the effective dynamics. The picture is stark on screen. A contracting cosmos compresses, the equations soften, and expansion re-emerges without an infinite spike. In ekpyrotic or cyclic pictures, a contracting phase smooths and flattens, then transitions into expansion, sometimes framed as brain-like surfaces approaching and rebounding. These models try to solve the horizon and flatness problems without standard inflation, or to explain inflation's initial conditions by making the prehistory do the smoothing. Bounce models face their own hard constraints, and the constraints are not philosophical. They are mathematical and observational. They must avoid instabilities, control anisotropy growth and contraction, and match the observed perturbation spectrum, including the delicate phase coherence seen in the CMB peaks. They must also explain entropy buildup across cycles, or show why cycles do not quickly become observationally inconsistent. Without such control, a cyclic story can drift into a universe that looks nothing like ours. A third family treats spacetime itself as emergent, not fundamental, which changes what beginning even refers to. In holographic ideas, spacetime geometry can arise from quantum entanglement patterns in deeper degrees of freedom, so distance becomes a derived notion. In some approaches, time is not primary, but an effective parameter describing correlations within a quantum state. Useful, but not fundamental. These proposals target the deepest version of the nothing question, because they redefine what it means for spacetime to exist in the first place. If spacetime is emergent, then nothing may mean the absence of geometry, not the absence of underlying quantum structure. Emergent spacetime ideas are powerful but currently underdetermined by data, which is both their allure and their frustration. They often reproduce known gravity in certain limits, yet struggle to make unique early universe predictions that would separate them from more conventional pictures. Their promise is conceptual, because they might dissolve the singularity by removing classical spacetime from the start. But a dissolved singularity is not automatically an answered origin, and the difference matters. Now we ask what counts as evidence, and what could actually discriminate models rather than merely decorate them. The CMB remains our best fossil record of the early universe's initial conditions, a cooled afterglow stretched into microwaves across the entire sky. Inflation-like scenarios predict nearly scale-invariant, adiabatic, almost Gaussian perturbations with specific phase coherence, which shows up as a precise pattern of peaks and troughs. Alternatives must reproduce those successes while leaving some distinctive deviation, because matching the CMB is not optional. We look for fingerprints in polarization and statistics, because the sky carries more information than temperature alone. Primordial gravitational waves would imprint B-mode polarization, setting the tensor-to-scalar ratio and the inflation energy scale, and offering a rare direct window into ultra-high energies. Non-Gaussianity tests whether fluctuations came from a simple single field or more complex dynamics, and it can reveal interactions that temperature maps hide. Running of the spectral index and features could hint at sharp events, multiple fields, or a pre-inflationary phase that left a subtle scar. Spatial curvature is another discriminator, because many models drive it toward near zero, and that near zero is itself a clue. A robust detection of non-zero curvature would reshape the inflation story and constrain no boundary measures, because it would point to a shorter or differently weighted early expansion. Large-scale anomalies, if confirmed as primordial, could point to boundary conditions or a finite beginning of inflation, rather than mere statistical flukes. The question is not only what we see, but whether the pattern is too structured to be chance. Relic particles extend the test window beyond photons, because the early universe was a particle accelerator that ran for a fraction of a second. Extra-relativistic species would shift the CMB damping tail and the expansion rate, constraining hidden sectors and reheating histories that set the universe's thermal starting point. Dark matter candidates can leave small-scale structure signatures, from warm, free-streaming cutoffs to isocurvature modes that would show up as mismatched fluctuations. Topological defects like cosmic strings would create specific CMB and gravitational wave patterns, thin lines of stress threading the sky. Primordial gravitational waves are also a target for new detectors, and the hunt spans very different frequencies. Space-based interferometers and pulsar timing arrays can probe stochastic backgrounds from phase transitions or cosmic strings, complementing CMB searches that focus on the larger scales. The detection would not automatically prove creation from nothing, but it would narrow the space of viable early universe histories. It would tell us that spacetime itself once rang like a bell, and that the ringing still echoes. We also confront the limits with the same honesty used in Chapter 1, because cosmology is strongest when it knows what it cannot claim. Even a perfect model of the Planck epoch might still assume laws and mathematical consistency, and those assumptions do not come with an internal receipt. Physics can ask why a given state evolves into our universe, but it may not answer why the laws exist. The question can shift from what caused the universe to what makes a law-like description possible, and that shift is both sobering and productive. If time begins, the demand for a prior trigger may be ill-posed, even if our intuition keeps insisting otherwise. Causes are relations within time, and a boundary to time is not an event inside time that needs an earlier event to push it. Some proposals replace before with a boundary condition, a selection principle, or a consistency requirement, which is a different kind of explanation. That move is not a dodge, but it changes what explanation means. Less like a domino chain, more like a constraint that shapes all dominoes at once. We synthesize the story we have earned across the series, and we keep the categories clean. The hot Big Bang describes a real early phase, not an origin ex nihilo, and its evidence is among the strongest in all of science. Inflation, if correct, explains the smoothness and seeds, but it likely presumes a prior framework, whether a field, a potential, or a quantum state. Reheating, baryogenesis, and dark matter show how much of existence is transformation, not creation, as energy changes form and symmetries break in specific ways. Transition. The closer we get to the beginning, the more our language becomes part of the problem. So did something come from nothing, in the strict philosophical sense, where nothing means no structure at all. Physics cannot yet say, because strict nothingness has no time, no laws, and no structure to calculate with, and calculation is how physics speaks. But physics can say that nothing in cosmology is rarely empty, and often means a lowest energy state with rules. It can also say that the Big Bang is not the first moment of everything, but the first moment we can robustly connect to evidence, with error bars we can defend. We end with a chain that links the abstract to the intimate, and we let the visuals carry the weight. Quantum fluctuations become density ripples, ripples become galaxies, and galaxies become stars that forge the chemistry of life, atom by atom in hot cores. Vacuum energy may drive acceleration at the beginning and the end, framing our history with two unknowns, an early push and a late drift. The mystery remains, but it is mapped by constraints and narrowed by every new measurement, every cleaner spectrum, every tighter limit. Final transition. The question of nothing is still open, but it is no longer unstructured darkness. The honest conclusion is a boundary, not a slogan, and boundaries are where science does its best work. We do not know whether the universe began from absolute nothing, from a quantum state, from a bounce, or from emergent spacetime. We do know what the universe did next, and we know how to keep testing the earliest moments with sharper instruments and stricter statistics. Curiosity becomes method, and method becomes the next theory that might finally explain what a beginning can mean. We followed the evidence backward, from galaxies and their redshifts to the microwave afterglow, and the light element recipe written in hydrogen and helium. That trail led us to a universe that began hot and dense, then cooled through inflation's growth spurt, reheating, particle phase changes, and the slow assembly of stars, planets, and life. And at every step, nothing kept changing shape. Empty space became a quantum vacuum, the vacuum became a dynamical actor, and the earliest moments became a boundary where our best equations stopped speaking clearly. We learned why the Big Bang is not an explosion in pre-existing space, but the expansion of space itself, a reconstruction anchored by multiple cross-checking observations. We also learned why that reconstruction does not by itself prove creation from absolute nothing, because the physics we can test already assumes fields, laws, and some notion of geometry. At the Planck scale, the singularity looks less like a physical point of infinite density, and more like a signpost that general relativity has been pushed past its jurisdiction. Inflation offered a powerful, testable way to smooth the cosmos and seed structure, yet it handed us new mysteries, including the inflaton's identity, the details of reheating, and whether inflation was a beginning or merely a chapter. Reheating and baryogenesis reminded us that even after the universe is born, it still has to become, converting energy into particles and somehow leaving a tiny excess of matter that did not annihilate away. Dark matter shaped the scaffolding of the cosmic web, while dark energy now accelerates the expansion again, echoing inflation's vacuum-like behavior and deepening the cosmological constant puzzle. So the story ends where it began, at the edge between what the sky can show us and what our theories can responsibly claim. Yet the edge is not blank. It is mapped with constraints, tensions, and predictions awaiting sharper tests. The central question was, if nothing existed before the Big Bang, no matter, no energy, no space-time, how did everything start, and what does nothing mean to physics? The most honest answer is that modern cosmology rarely uses nothing in the absolute sense, and when time itself begins, before may be as undefined as a point north of the North Pole if there is a deeper description behind the boundary, whether a bounce, a no-boundary beginning, a tunneling event, or emergent space-time. It will not be confirmed by rhetoric about something from nothing, but by signatures left in the universe we can still observe. That is why inflation's fingerprints matter, from the exact tilt and smoothness of primordial fluctuations to the hunt for B-mode polarization and primordial gravitational waves, and why the details of reheating and hidden sectors quietly reshape what we think the early universe allowed. It is also why unresolved tensions like lithium's mismatch and the Hubble constant disagreement are not embarrassments, but potential doors into new physics. In this light, the opening hook changes meaning, because the first fuse may not be a spark in time, but a boundary condition, a quantum transition, or a principle that only makes sense once time and geometry have already emerged. Physics can tell us what the early universe was like, how it evolved, and which origin stories are compatible with the sky, but it may never translate absolute nothingness into an equation without smuggling in structure by another name. And still, the journey from that boundary to us is astonishingly coherent, because tiny quantum jitters became patterns in the microwave sky, those patterns became galaxies, and those galaxies became the chemistry that can ask where it came from. The universe may have started from nothing, or it may have started from a kind of something too primitive for our words. But either way, the deeper lesson is the same. Mystery is not a dead end, it is a landscape, and evidence is how we learn its contours. If time has an origin, then beginnings are not just moments, they are limits, and limits are where science grows most carefully. So perhaps the most memorable answer is not a final explanation, but a reframing. The question is not only how everything began, but how far the universe lets us look back before how becomes, what does the question even mean? In that sense, nothing is less a void behind reality and more a mirror held up to our assumptions, reflecting the difference between emptiness, vacuum, and the edge where space-time itself may stop being the stage. If you want to keep following that edge, watch the next generation of measurements, from CMB polarization and galaxy surveys to gravitational wave backgrounds, and ask which predictions survive when the data gets sharper. The opening asked what lit the first fuse, but if time begins at the Big Bang, there may be no before in which a fuse could wait. In modern cosmology, nothing is rarely absolute emptiness, and the real question becomes which boundary description best fits the evidence we can still read in the sky. We may never hold absolute nothing in our hands, because the moment we describe it, we give it structure, and structure is already something. Yet the universe has left enough traces to turn ignorance into inquiry. So the darkness before the first light is not empty, it is where our next map begins. If this mystery moved you, follow the evidence as it improves, and keep asking which origins are testable and which are only stories in scientific clothing.